वाईफाई वाईफाई अब हमें चाहिए ये आनंद सिलेक्ट हो भाई किचन में था तो है आनंद से ये अब आनंद पकड़ो ठीक है मैं वाईफाई तो दूंगा ना इसके हो गया हाँ माइक तो ऑन है कैमरा नेक्स्ट टू we have things under control. Where is the representation? And this is so. Okay, it's never a perfect moment to get started. There'll always be some technical glitches, right? So welcome all of you. I'm Ramanan Chakravarti. I'm from the Center for Earth Sciences out here. And it's technically Earth Day. I don't think there's a better day to talk about Mars, right? And so let's kickstart our workshop, which we call it Mars Science Workshop, being very creative. Put it, I think Martin was responsible for the tag in the Mars Science Workshop to just make it different, right, Martin? So this history, came around 6 months ago. The discussion, I think Shama messaged me, Shama and Martin had a discussion, and then they said, hey, would you guys like to host? And we said, why not? Because there's always a partner that was a planetary scientist a while ago, so it was exciting. And it eventually, I think, started in traction maybe in the last 1 month, and a lot of help from Curtin, a lot of help from ISRO, and of course, a lot of help from my students and colleagues and postdocs. So we are particularly happy that, despite all the geopolitical situation all over the world, people have been able to travel from other countries. There was a time when Martin was supposed to be here, then there was a time when there were some cancellations, and there is, again, a good time to visit. So things have come together. So I think, the idea of this workshop is to basically bring together a community that is interested in planetary science, particularly on Mars, but just to provide a platform. And so when I requested all the speakers, I said, keep your talk a bit pedagogical so that there are students who will be there in the audience who might be interested in listening to your talk. Of course, you can talk a little bit about what you are doing. And so we also have been sending out, a registration link to a lot of students and colleagues all over the country. And it turned out there are more than 400 registrants now, and which is a big number. And so what we've done is there are some YouTube live streaming links. So there are 2 students who are not here, but they're actually in my lab, controlling the system with. We don't have technical support, so it's just students and postdocs who do everything. And so we will have a bunch of them join on YouTube Live. But unfortunately, we couldn't allow everybody to be on Teams and have Teams crash, which might crash anyways, okay? Because it's Microsoft, right? I mean, and so we have the Teams link sent to all the speakers and slightly more, I wouldn't, make it an age bias, but maybe more experienced scientists, so that in case there are discussions, they can, take part. And but students have the flexibility to also write their questions on the YouTube Live link, and so hopefully the dream is to eventually circulate it around among the speakers and give them some responses. So anyway, long story short, we have on day one, so 2.5 day event, and day one is primarily, the first half, at least at the coffee break. In the afternoon, we have mostly, deep planetary evolution, those kind of flavors. And of course, we have a bunch of online talks and only 2 in-person talks until the coffee break, after which we have a couple of talks on very different flavors, astrobiology, and then of course, Martin's talk on hot springs and again, origin of life. So we wanted to start off this discussion with a general overview talk by Stephen Ruff. And Stephen had a different, he'll be presenting another talk later, but he had a different talk title, and we kind of requested him to make it a little bit more general, and he thankfully agreed. And so thanks a lot, Stephen, for being accommodating. So no more talking, let's get started.
Is someone going to drive the... Okay. All right. Can you hear me all right? Okay. Okay. All right, great. Well, thanks for everyone coming. I thought it would be nice to start this workshop with a bit of an overview, a real general sort of overview about Mars, with the assumption that not everyone here or online is a Mars expert. So I was hoping to kind of present Mars in a big, almost literally big picture kind of way, so that we can all at least have maybe a common starting point. So let's see if this is going to work. On the keyboard? Good. All right, so talking about the history of Mars, I thought we should talk a little bit about the history of the people who studied Mars. And I like to start these kind of talks with going way back to some of the first really scientific observations of Mars. And Galileo, the astronomer, is sort of credited with being the first person to point a fairly new invention, a telescope, at the surface of Mars. He was aware, for example, of Venus. The planet Venus shows beautiful phases through a telescope. So he was looking for phases of Mars, but because it's beyond the Earth, it's pretty hard to see changes in the phase of Mars through a telescope. Huygens came along later, was able to look at these dark and lighter toned areas on the surface of Mars and recognize the different markings and polar caps. You can see these lighter tone whitish materials on the North Pole there. And then you can also, over time, document the rotation of Mars through these markings. So that was in the 1650s, roughly the same period of time. The Italian Cassini was first to note that the polar caps, he could see those for the first time, and then was also able to refine that orbital, the rotation of the planet on its axis, to recognize a Martian day that we call a sol, by the way. And it was Herschel who really refined all of this to recognize, this is pretty remarkable in the 1700s with a telescope, to recognize the length of a Martian day to within 13 seconds of what we know today. And so if you don't know, the length of a Martian sol, a Martian day, is remarkably similar to Earth's. It's a cosmic coincidence that it's 24 hours and about 39 minutes or so. So the length of a Martian day is remarkably similar. You can look at the moon, and the length of a day on the moon is a month. And Venus, its day is longer than it takes for it to go around the sun. So the length of a day on Venus is longer than its year. So Mars has this benefit really for us and for our exploration of having a day that's very close to ours. Schiaparelli, Italian astronomer in the late 1800s, was the first to use a scope and to recognize these sort of lines on the surface that he termed canali. And the Italian word canali really just means channel, not canal as we think about it today, being something that's created by humans. So Schiaparelli somehow was seeing these features called canali crisscrossing Mars. And based on that kind of result, there was Boston, a wealthy Boston man, Percival Lowell, who came west in the US looking for a good place to build an observatory. And it happens to be in my home state of Arizona, up north where high elevation and dry creates good seeing for astronomers. So Percival Lowell created the Lowell Observatory so that he could look for Schiaparelli's canali. And sure enough, Lowell was able to see these features in even more detail, and so created these maps of Mars, beautiful color in this case, hand-drawn, with these features that to his eye, and this is what's important here, was recognizing not only channels, but was actually calling them canals. So this was an era when, at least in this case with Lowell, the idea that not only was there life on Mars, but there was intelligent life capable of creating these large structures. This was in the popular culture of the era. There was astronomers, most astronomers of that time didn't see this and didn't believe this story, but there was enough popular excitement. It even generated sort of a craze at that time. And this is exactly when, essentially in the same period of time, H.G. Wells wrote The War of the Worlds, this concept now based on science. This is truly science fiction, right? You know, so this is based on some astronomer seeing something on Mars that creates this story now of a civilization trying to bring water from the poles and ultimately coming to Earth. So we know all this is wrong, right? And it took, you know, there was more astronomical observations in the subsequent years, but it really took these early NASA missions. The Soviets at the time were also flying missions to Mars with much less success. But in this case, this was the first flyby. And NASA, over its history, has always followed this path of you do a flyby mission first because it's easier than going into orbit. So these first missions to Mars were like this. They were flyby missions. And in this case, some of the very first images of Mars, very grainy television camera images, essentially, were showing craters for the first time. Those telescopic observations, there's no telescopes on Earth that are good enough to see craters. So this was a bit of an eye-opener for scientists at the time that there was a cratered surface like the moon. A subsequent set pair of flyby missions both were successful with better spatial resolution of those cameras. And in this case, they showed this cratered surface in even more detail. You know, so here's a time of Mars exploration when it was thought that Mars had potential for vegetation even. There was an astronomical feature called a wave of darkening that was probably now we recognize related to dust coming and going. But there was a time, even in the 60s, when it was thought that Mars might have vegetation, but this started to sort of reset that thinking. You know, here's a planet that's showing these craters preserved like the moon. So Mars was becoming a more moon-like place. The first orbiter, so I was saying you start with flybys, and the first orbiter happened in 1971. And of course, when you go into orbit, that gives you much longer time period to observe not just a portion of the planet that you fly by on, but you can observe the whole planet. And in this case, this was the first time now seeing something other than craters. You know, those first flyby missions happened to fly by some of the most cratered terrain on Mars. But this was a case where, and by the way, this was the era of actual cutting and pasting to make mosaics of images. And so you're seeing this fairly primitive approach. But now for the first time, here's a large canal channel. So this is some kind of water cut, and there was a lot of debate early on whether water was the agent of the erosion here, but ultimately it's been determined that Mars, and I'll talk more about this later, has these outflow channels that were now being imaged and sort of resetting again the view from Mars as moon-like to something not moon-like. The moon doesn't have any features like this. And then finally, the last of these that I'm going to show is the Viking 1 and 2, both orbiters and landers. NASA used to do redundant missions. They would send 2 of everything in case one of them failed. In this case, all 4, both 2 orbiters and 2 landers, and the landers are in this shell underneath, an image of that. They were all successful. And this is an era when the great Carl Sagan, a still frame from Cosmos series that appeared on in the 8 so time frame, and you can scale. This is the scale of that first. There was 2 landers, plutonium powered landers that in terms of electricity generating electrical power, and these missions actually had light detection instruments on board for the first time. And we haven't subsequently done that, like detection instruments. So this was a remarkable capability. And here's one of the earliest images of Mars with the sky that looks very not moon-like. You know, there's enough of an atmosphere on Mars, and I'll talk about its atmosphere a little bit, to create a dusty sky with that color, and then dust-covered rocks in the landscape. So it was an earliest views of the surface of Mars. Okay, so I want to kind of step back now and talk about Earth versus Mars. And so I'm showing the 2 planets at essentially their actual scale relative to each other. So you can see Mars is quite a bit smaller than Earth, which is an important kind of, ultimately, it has some role in controlling its geology, for example. The length of a Mars year is a little less than 2 Earth years. So to go around the sun, it's roughly, it's a little less than 2 Earth years. The Martian day, which I mentioned, is very close to an Earth day, and we call it a sol just to distinguish it from a day. So when you hear the rover teams, they talk about sol number X, Y, and Z, and it's just a convenient way to discriminate between an Earth day and a Mars day. And because it's so much smaller, the gravity of Mars is only about a third or so. I think it's about 39%. Of Earth's gravity. So that's actually a benefit for trying to land on Mars, but it still has many, many more challenges. The atmosphere of Mars today, compared to earlier, is very thin. So it's less than 1% of Earth's atmospheric pressure, and what's there is mostly CO2. There's really good observational evidence from the MAVEN mission, another NASA orbiter, that shows that Mars probably had about a 1 or 2 bar atmosphere, so 1 to 2 times Earth's atmosphere early in its history in the first billion years or so. And it lost its magnetic dynamo, so the magnetosphere went away, and over billions of years, solar wind sputtering carried a lot of the Mars atmosphere away to get to what we have today. So it's a very thin atmosphere. And because of that thin atmosphere, the temperature range is quite dramatic, even over the course of 1 sol. But this is sort of the broad range for the whole planet of temperature, roughly minus 125 to 25 C. Cold enough that the atmosphere, the CO2 atmosphere in the wintertime at both hemispheres will condense CO2 out of the atmosphere. So dry ice precipitation in the polar regions in the wintertime. All right, so this single sort of map from the Mars Orbiter Laser Altimeter. So this was, you can see the year that this was published. So this was on the Mars Global Surveyor. And so it was using pulses of laser, I think 1 micron laser wavelength to pulse the surface like radar, but it's more of a LiDAR approach. And so this map took actually probably months, if not a year, of observations to build up this incredible topographic map of the whole globe of Mars. Of course, you're seeing the whites and the reds are the highest elevation, and the blues and purples are the lowest elevation. And just for a sense of scale, I couldn't resist for those who need that, and also an actual scale bar, so 2,000 kilometers. So you can see some of for me, I can stare at this rendering for hours. It's just so filled with information. And obviously one of the most obvious things that you can see are these huge impact basins. You know, here, there's another one here, even that deeper blue up there. And then the whole of the Northern Hemisphere. You know, this map shows what previous missions and observations were seeing, this dichotomy, a global dichotomy between the highlands of the south and the northern lowlands. And so this really nicely displays that. And the thinking right now is that whole bluish area in the north is part of a huge impact basin called Borealis Basin that formed early in Mars history. There's still debate about whether this dichotomy includes evidence for plate tectonics. You know, plate tectonics is a feature of Earth. It's the only planet so far that we know has this process of recycling the crust, which is hugely important for all sorts of things. Mars, there's still debate whether Mars got started with plate tectonics and it failed, or if it ever started at all. The other sort of aspect of this, the southern highlands is very densely cratered. So those early flyby missions, we're seeing this densely cratered surface versus the less cratered in the north. And the very fact that you're preserving impact craters like this over billions of years is a very clear distinction between a planet like Earth with plate tectonics and the recycling of the crust. You'll never see something like this on Earth because our crust is constantly being recycled. Mars is preserving craters for billions of years. So it's a very different environment. I want to go to a portion of Mars that has a lot of interesting geology going on, as well as sort of telling the story about aqueous processes on Mars. So I mentioned early in this talk the outflow channels that were recognized from the Mariner days. And so here you're seeing, and again, look at the scale bar, you're seeing these outflow channels, catastrophic formation. It's still sort of unclear how huge flows of water scoured the surface. Where did that water come from? How is it released so quickly to allow these incredibly huge outflow channels? And you can see it streaming off into the northern lowlands and the Streamline Islands. And here is a clear feature on Mars that's related to some kind of tectonic activity. This is the Valles Marineris system. And I come from the state with the Grand Canyon of the US, and that would be the equivalent of one of these little side canyons here. This would stretch from about LA to St. Louis, Missouri. Huge canyon system that is mostly related to some kind of tectonic activity, but then mass wasting, just the gravitational failure of the cliffs along that scarp. How am I doing for time? I haven't kept track of time. Is someone? Okay. Okay, so this was sort of the introduction to the aqueous part of the aqueous history of Mars. You know, this is just one early example, early for Mars, of what is now accepted as flowing water on the surface of Mars. This next image, which is actually a mosaic of images from the Mars Orbiter camera, the Mach camera. This for me was a really exciting discovery. This is, so Malin and Edgett, they're colleagues of mine, they're very conservative with their interpretation and just called it an alluvial fan in the beginning. But over time, it's now been accepted. This is an actual delta deposit that was formed at the interface between a standing body of water and a river going into this crater called Holden. And one of the remarkable features here is, for geologists, geomorphologists, you can recognize this cutoff meander. So you're seeing in this landscape literally the action of flowing water slowing down enough that it creates a new meander. Well, actually, the old meander is the upper one, and then it cuts off that older meander to create this cut-off meander. And so this was a really beautiful example of not only flowing water on Mars in its early history, but with enough time for that flow to generate these kind of deposits. Like all good scientists and geologists, there's a debate still about how long it actually took to create this delta. It could have been anywhere from hundreds of days to many years. So there's sort of still a debate about how long it took to make that landform. There's other evidence for water on Mars. How young this is. I think it's on, I just looked this up, I think it's on order of 3 to 3.5 billion years ago. So someone is nodding. So yeah, I think it's still very old. I think it's, Hesperian age, early Hesperian, but early to mid Hesperian. So 3.5 billion years ago is, I think, the accepted number. Okay, so mineralogic evidence for ancient water. I get asked this a lot about, was there really water on Mars? And as a geologist and someone who studies mineralogy, there's so many minerals that have been identified from orbit with, mostly it's a combination of the CRISM, and which is a US infrared mapping spectrometer, imaging spectrometer, and then the Europeans' Omega instrument. And there's some from the instrument I was involved with, the TESS instrument. But the point is, all of these dots here are showing minerals that essentially on Earth require water to form. They don't necessarily have water in them. Some of them do, but they require some amount of water to form. So, and of course, the scale of these features is not the size of the dots that you're seeing. So there are all of these places on Mars that show from early in Mars history the formation of water-related minerals. So this is a clear, again, departure from the moon, for example. You're never going to see this kind of mineral map of the moon because there's just not water to do that. So this is really clear evidence. And one of the things I want to point out is some of my early work shows using infrared mapping the distribution of dust on Mars. So all the red areas on this map are very dust. They have abundant dust. In fact, using a different technique, thermal inertia, we know that the core of these red continent-sized features can have dust that might be tens of centimeters to a couple meters. So these places on Mars are filled with dust. And of course, you can't, with the infrared techniques, you can't see through dust. In fact, you can't see through even a millimeter of dust with an infrared orbiting spectrometer. So the fact that you don't see dots all over the place is in part because you can't see the surface through the dust. Can you what? Yeah. Yeah, they have to be. So it's not a subsurface technique. So this map is literally seeing the top micrometers of the surface. Yeah, but did it? No. So the answer is some of these occurrences actually formed somewhat at depth and have been exposed. So it's a combination of stuff that was formed at that elevation and others where erosion has exposed it. Yeah, good question. All right. All right, so the time of this, so I've talked about sort of ancient processes, ancient geology, ancient aqueous processes. And here's sort of this comes from great work by Bethany Edelman et al. And so here you're seeing on the x-axis the scale in billions of years from the formation of Mars up until the current. And there's even sort of a gap here because not much happened in the most recent years. So you can see that most of the volcanic activity, those huge volcanoes, I actually forgot to point out the huge volcanoes, didn't I? That's unfortunate. So Mars has the biggest volcanoes in the solar system and associated mostly with this Tharsis plateau or mound. And so most of the volcanic activity was happening early in Mars history and dying out. Same kind of story for the water on Mars. Most of that surface liquid water was happening in the earliest history of Mars when it was warmer and wetter and can support liquid water. Today, liquid water would boil away. If I had this bottle sitting out on the surface of Mars today, it would essentially boil away within a few minutes. So there's not enough pressure to keep liquid water on the surface stable today. And you can see this effort to kind of demonstrate that there was episodic sort of pulses, and it's still not fully clear what those pulses were, whether they were impact generated or related, or if volcanic activity filled the atmosphere for short periods of time. So there's a couple different scenarios for how you can have this waning stage, sort of ephemeral pulsed water, even into the Amazonian period. So there's evidence that liquid water has been active on the surface of Mars, but in these much more discrete periods of time. All right, but modern Mars, there's still geology and water-related stories that happen, and Mars is truly the dune planet. So there's sand sheets on Mars with basaltic sand. Many craters have this kind of crater floor unit of abundant basaltic sand dunes, and one of my favorite early images, early from the 2000s, these beautiful basaltic sand dunes, and rather than a scale bar, I love to show the pyramids of Giza and how huge these basaltic sand dunes would be if they were here on Earth. Most sand dunes on Earth are made of quartz, and this is yet another kind of legacy of the absence of plate tectonics. The reason we have so much quartz on this planet is because the granites that formed at depth are delivered to the surface and eroded. Granites have a lot of quartz. Mars probably has granites at depth, but they're without plate tectonics to bring them up to the surface. You end up with most of the material that's available for sand dunes on Mars is made of basalt, not quartz like on Earth. Mars also has incredible dust storms. Even with that very thin atmosphere, you end up with these kind of, you can see the scale, this huge dust storm. And several years ago, I was flying back into my home city of Phoenix, Arizona, and from the window of the plane, I looked out, and you may have seen stories out of Arizona and Phoenix about, we use the Arabic word haboob to describe these ground-hugging, they aren't sandstorms, it's really dust, so this likely same kind of feature that we see even in Arizona and elsewhere. And then the dust on Mars has this ability, you can see there's smaller versions of dust storms, but every few years, 3-4 years or so on Mars, Earth years, you can generate these globally encircling dust storms. So there's still some uncertainty about what processes. Mars has dust devils, these swirling vortices, as well as those larger haboob-like dust storms. But somehow dust can be lifted, and it's key. This is not ground hugging to go from, these are Hubble views you can see the time there. So what you're seeing is not a ground hugging dust across the surface. The dust can go high into the atmosphere and circle the globe. And so global dust storms are a real issue, both for rovers that are solar powered and this can take weeks to months to clear the dust out of the atmosphere of Mars. The last thing, how am I doing for time? Okay, I'm gonna wrap this up. So modern water ice is really an interesting story about Mars. And this comes from the neutron spectrometer on the the Mars Odyssey mission. And so basically you're seeing hydrogen abundance. So hydrogen is a good absorber of neutrons. And so this is a case where you can see hydrogen abundance going from low to high. In these higher latitude blue areas, so much hydrogen there that no mineral, there's hydrogen in minerals, OH and H2O bearing minerals can take up hydrogen. But in these places on Mars, there's so much hydrogen that the only mineral that can have that much hydrogen is water ice. And this is a great story of, this was a place, let's send a lander to this place on Mars, the Phoenix lander that I'm going to show in a minute, and test this hypothesis. This is a beautiful example of science in action. So here's a rendering of the Phoenix lander. You can see, and I'm showing this on purpose, it used retro rockets to get to the surface. And it turns out those retro rockets were good excavators. I should mention that this map can only sense down about a half a meter or so. So this map is not seeing deep into the surface. This is only seeing about a half a meter or so into the surface. And so here's the view underneath. The robotic arm had a camera that could look underneath the rover, so you're seeing the landing legs. This is pure water ice right here. So those retro rockets blasted away, several centimeters of Martian regolith to expose this white stuff underneath, and elsewhere it was within the landing zone. It was confirmed that that's ice, exactly as that hydrogen mapping was suggesting. And so Mars at the high latitudes today has water ice. And the polar caps, we've known since the astronomers in the 1600s. And here's just a nice sort of oblique view of these layered, it's water ice here layered with dust. So you can see, and dunes there out on the side. Here's the South Pole. Also, the permanent cap is much smaller. It's roughly almost identical to the size of Iceland. So these are the permanent water ice caps of Mars. Again, in the wintertime, there's CO2 that can condense out of the atmosphere, but then that goes away in the spring. All right, last kind of summary here. Unlike Earth, meteor impacts have happened on Earth throughout its history, but the evidence of that is not preserved as it is on Mars, and it really is that absence of plate tectonics that allows meteorite impacts to stay preserved. Volcanic activity, and again, I'm sorry I didn't show the huge volcanoes on Mars. Huge volcanoes, lava flows have resurfaced large parts of the surface of Mars. The aqueous activity, as that timing showed, was much earlier, but there's still evidence of water throughout Mars history, and certainly there's water ice today. I sort of already said that. And wind is kind of the dominant, unlike Earth, where water is the dominant agent of erosion. On Mars, wind in the current environment, and mostly in the last few billion years, wind is the agent of erosion, with water also having a role in the sort of geomorphic expression of Mars. So that's it. Thank you.
Hi, Steve. Thank you for the amazing talk. My question is very naive because I'm not an earth scientist, but would be an answer probably everyone knows. What's the technical difference between a dust storm and a sandstorm?
What's the difference between a dust storm and a sandstorm? It's just the particle size and the way that the grains get moved. So sand grains tend to be 100 microns or bigger. There's probably some slight. So sand grains move by bouncing along the ground. It's called saltation, where one grain bounces and it flips up another grain and another grain. So that's a chain reaction of bouncing. Dust storms usually have the dust on Mars in the atmosphere is only a few microns in diameter, and it can be carried in suspension. So it's not bouncing along the ground, it's carried up in suspension. Okay.
In the mineralogy map which you showed, I find that most of the minerals are all found around the equator, and the polar regions are sparsely spaced. Is that because we don't have enough observations, or is it?
Yeah, it's a good question if there's an observational bias or if that's real. I don't have a really firm answer. I think it's. I think there's some combination of. Yes, the higher latitudes aren't as well exposed, and they have, for sure in the Northern Hemisphere, it's been resurfaced since it was originally formed as its huge impact basin. So it's probable that any of the kind of water-related minerals in the Northern Hemisphere have been buried under lava flows. And then the Southern Hemisphere is a little more dusty. So it's some combination of, I don't think it's an observational bias, I think it's just the bias of Mars, what's exposed or not.
Because the reason given for appearance of these minerals are that there is a requirement of water, presence of water. Whereas when you see the distribution of water, the last map which you showed, the polar regions are largely having concentrations of hydrogen, and there's a higher chance of water presence in the polar regions.
Yeah, but
so there is a contradiction. Like,
well, so So the high latitudes that you see, the hydrogen abundance, that's near surface water ice that formed, pick a number, in the last billion, million, it's recent water ice that probably comes and goes. I didn't talk about the obliquity changes on the planet where the poles become exposed to the sun and then away as the planet tilts. So the water ice that you see today isn't really capable of generating the kind of kind of water-related mineral that map was showing. It's modern ice, very, very cold environment where only thin films of water, liquid water, are available, and you don't make many minerals in that fashion. Does that make sense? Okay. All right.
I have a technical question. The map shows for water or hydrogen. I think that refers to water equivalent hydrogen rather than the hydrogen itself, because the concentration is 4%. So as you know, that one weight percent water is weight percent equivalent hydrogen. So can you clarify that?
So we're having a hard time hearing you. So if you can type in your question, we can come back to it later. Thank you.
Yeah.
Okay. More questions. Have one talk that is not going to happen. A bit of time for. Anyway, we're trying to keep some 15-20 minutes prior to lunch every day for discussions. So if you have more questions, please hold on to your questions for now. The next talk is actually an online presentation by Dr. Katerina Nukovic from Curtin University. Katerina, can you hear us?
Yes, I can.
Yes, I can. Hello.
Could you share your screen, please?
I can also hear myself.
See, there is some issue. Okay, because it's talking about voice.
Okay, there seems to be some audio issues for people speaking virtually. It wasn't there yesterday. So Katerina, can you just speak a few words?
Yep. Can you hear
me okay?
Just give us a minute.
मीटिंग चल रही है फाइनली there was some
Can you speak now, Katerina?
Yep. Hello.
Yep. Hello.
Does that look okay on your end?
There's a bit of echo that's happening, so we're trying to figure that out.
I think now it is fine.
Because we tested out. Can you put your mic a little bit far away from you and just check it? Because
is this better?
Is this better?
No, it's the same. Can you mute your mic in the room? Can you hear me okay now? Can anybody online hear me?
Yeah, now it's better.
Okay, so if you keep the mic muted in the room, then I see that people online can hear me. So I'm assuming that people in the room can hear me too. Okay. I'm going to start if that's okay with you in the room. I can't hear you, you're muted.
It's better now. I think we are not having problem.
Okay, let me know when to start.
Siddharth, I think you were messaging. Can you? Right?
Do you want me to start the room?
No. Arunava, can you just say a few words?
Hello.
Hi.
Hello.
Hello.
Yeah, speak up a bit more.
Hello.
Hi.
Am I audible now?
Audible now?
Yeah, you are audible, Arunava. Can you speak up one more time?
Hello.
Hello.
Okay, I'm going to shut my mic off, then speak, Arunava.
Okay.
Okay.
Yeah. Okay, Arunava, on a count of 5, can you speak something, okay?
All right.
Hello. Is that okay? Can I from the room? I've got thumbs up online. Is the room happy? Wave at me.
Wave at me, I can see.
Great. Thank you. Thank you. Just mute the room. Okay. Hello, everyone. From Ananda, please mute. Okay, we're good. Okay, I'm not hearing any echoes. I'm assuming everybody can hear me. Great. Hello, good morning, everyone there. I'm terribly sorry for not being able to be there in person, but I was looking forward to participating nonetheless. So I'll try to keep this as brief as possible, yet informative, especially for all the students that are following this online and in a room. So this short lecture is about Mars interior structure and lessons learned from the NASA InSight mission. Probably a little bit about from the very beginnings to the very end as to what we have learned. So you don't see me in the room. This is me in the middle calling from Perth at Curtin University and our School of Earth, Planetary Sciences and Space Science and Technology Centre. So from Steve earlier, a little bit of background on our understanding of Mars in the past aqueous climate and conditions. I would like to take you on a bit of a journey around what we have learned through geophysical investigations. So prior to the NASA InSight mission on Mars, there was, I want to say myriad, but not myriad. There were a handful of missions that have roved on the surface, landed on the surface, and searched for search for signs of life and past water. We had a lot of remote sensing activity in orbit around Mars that have looked down on the surface and captured the surface geological features in high detail, as well as some of the transient effects. So we know that very well. What we don't know is what's really on the inside of the planet that much. So prior to InSight, we wanted to know how warm or how active is Mars. Is it more like Earth or is it more like the Moon? By size, it's somewhere in the middle. I am trying to move my slides, but they are not progressing on your end. Look like you're stuck on slide 3. Is the connection okay? I have moved the slide, but you don't see it. Okay. I'm advancing slides on my end, but I can see your screen is not changing in your room. I don't know. Can you guys online see Moon, Mars, and Earth globes right now?
Can you just stop sharing and just share it again?
Okay. Online people can follow. It's just
yeah, the virtual people can see it, but
the room doesn't see it. Okay, no problems. I will do that in a tick. Okay, that should be fine now. Sorry, there is a big lag. You only see my cover slide, and I have advanced the slides.
Leaving and joining again. Now it's moving.
There we go. Great. Okay. So this is what I was saying. We wanted to know how warm, how active is Mars as a planet compared to Earth or the Moon, which are the other two planetary bodies we know a lot more about its interior. So what do we know? There we go. There is a lag. Okay, gotcha. Okay, so we know that on Mars there is Valles Marineris, which is the largest canyon in the solar system. And we also know there are big shield volcanoes like Olympus Mons that is 2.5 times the height of Mount Everest, and the surface area is the size of France. We don't have geological structures on Earth of that size like they exist on Mars, but Mars is a much smaller planet. So just think a little bit about that. What are the kind of interior motivations that made Mars the way it is? The InSight mission wanted to learn about the size of the core and the structure of the core, as well as the thickness structure of the mantle and the crust, and also how warm it is in the interior. The mission itself took decades in planning. As you know, the space exploration and missions take pretty much a whole human lifetime. It was eventually built and launched in May 2018, even though it was pegged for launch 2 years prior, but there was a problem that needed to be, then the whole launch needed to be postponed. It took about 6 months, 6 to 8 months to cruise to Mars, where it landed in late November 2018. And after a few months of engineering operations, when the seismometer was put on the ground next to it, we started science operations on the surface. Here is just an example. On the left-hand side is a selfie of InSight a few days into the mission, nice and clean, properly set up for operations, and with a full power consumption through its solar panels. And then what you mean now, it's basically 2022, 4 years later, at the end of the mission, where you can see the whole spacecraft, but more importantly, its solar panels got caked in the Martian dust, and solar radiation could not really penetrate to that dust, and it couldn't charge the batteries on the spacecraft, and operation had to be completed. But I'm actually happy to report that this also happened about 4 years into the mission, which was actually planned end of the mission anyway. InSight landed in a place called Homestead Hollow. It's a degraded small crater in the equatorial region of Mars. What you see is almost a full view panorama. A place nice, flat, and boring, which is perfect for seismology. Geologists gave an interpretation of the immediate top crust structure to about a few meter depth to about 10 meter depth about the boulder structure underneath, immediately under the lander. And in terms of what kind of seismic activity we could expect to see on Mars, well, from geological structures we observe on the surface, we know that there are small tectonic activities from like small young tectonic faults that are appearing on the surface. Potentially some rumbling magma in the interior chambers as well, even though that we do have surface lava flows, but they're all millions and millions of years old. So we don't expect to have active and frequently active volcanic activities, but certainly magma rumbling in the interior is not impossible. Also impacts, because meteorite strikes happen on Earth, they happen on the Moon. We know that cratering is a standard process, standard geological process on all planets, as well as Mars. Interesting thing about impacts on Mars is that they, yes, they happen, but because the density of Mars's atmosphere is 1% of the Earth's gravity, that means it does have an atmosphere just dense enough to mess up with the with incoming meteoroids, but not enough to fully ablate them. So in 50% cases, we get single strikes on the ground. And in 50% of the cases, when we have a fireball in the atmosphere, they actually burst, but they burst very close to the ground and they pepper the ground in a cluster shot, which complicates seismology. Here is an example of a cluster impact. So this is a single strike on the surface, but the projectile basically fractured close to the ground and peppered the ground in multiple shots. We were expecting to see maybe a few tens of impacts over the course of the mission. What you see here in the white dots were fresh craters formed in the last 20 years, and kind of the bullseye target marks the distance away from the seismometer, meaning that the smaller impacts are only visible seismically from closer distance, and if they're bigger, then they can be seen from a larger distance, but they're less frequent. We were very, very pleased when we got the very first impact that happened only 37 kilometers away from InSight. And that's literally like rock falling on our heads, you know, considering how big the planet is. You know, some would call it a walking distance almost. But even though it hit 37 kilometers away from the lander, we saw that from orbital imagery. The rock that made a 1.5 meter crater is only 4 centimeters across, and it did not create a significantly big quake or mass quake to be detected in our data set. So close, but no cigar at that point. We did a lot of modeling trying to understand the impact cratering process and coupling with seismic progression towards the detector, but that particular impact did not get detected. For a very long time, about 1.5 years, almost 2 years into the mission, we thought we were just simply unlucky, or that signal to noise is too low, that we can't really see impacts because the time went on and we only had that one tiny impact. we thought maybe there is not that potentially we're not really seeing the family of events that are associated with impacts from the entire Mars-Quake database, or that we simply don't see enough from orbit. So what ended up being true is the fact that we needed more data to be able to start seeing them between different families of seismic activities. There were 4 impacts were recorded by doing a back search, really backdated search through the Mars-Quake database in 2020 and 2021. That were 2 of them were single strikes. One of them was a cluster shot. You can see this one here is like 3 shots, boom, 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 like one after the other towards left and right. And that was a grazing impact that fractured as it fell on the ground and made 3 or more separate impacts. There's one more here that you don't see in the picture that was an airburst, cataloged as airburst. More details about that big clustered shot. I'm not going to even try to run this because in case you can hear it or not, but it's basically a combination of ground strikes and airbursts that splits across frequencies. Then about a few months towards the end of the mission, we actually got 2 really large impacts of the size that we never thought we would get such large impacts. We thought the largest impact would be about 20, 30 meters. We got the one that was, they were over 100 meters across, these 2 events, and they were halfway across the planet almost. Here is an example of before and after image, a very clear, very large, small, fresh crater. And to look at it in a bit more detail, what you see here, I don't know if you can follow my mouse, but basically the separation A is a forbidden zone, showing that this is the direction where the impactor came from, creating these long scimitar rays marked as C that are shock front, and then the bulk of the ejector, the biggest fragments going downrange, where you can see it as marked D. And the crater itself is about 150 meters, and it had excavated ice. So the exciting bit here is that the ice fragments were excavated from about 6 to 10 meters depth. They were not shocked or not changed by the impact itself because they came from particular depths that are not affected by the shock. There's not a lot of shock anyway. And there was some heating in the bottom of the crater, which is why you don't see any ice in the bottom of the crater, but you see it in the ejector rays. The good thing about it is that this is the most sudden, and this is an example of a bad map, but this is where the crater is in the Amazonas Planitia, in the region, this kind of mid-polar, mid-latitude region where we believe to be between the discontinuous and continuous ice layer underneath the regolith. So it's the southernmost impact crater that had excavated ice ever that's been recorded on Mars, and we have a quake for it too. This is just the result of some numerical simulations that suggest heating and the depth of excavation. No time to go into too much detail about it, but nonetheless, constraining the properties of the impact conditions, so properties of the impactor and impact conditions that are observed from orbit. We know how big the crater was made and when, so we can model that. And then also we have the quake that it made so that we can then go back and deconvolve and understand the interior structure of the top crust between the seismometer and the impactor. And so with that, we concluded about that on average, on that region of Mars, there's about 200 meters of regolith, and the depth of fractured rock is about 20 meters of regolith and about 200 meters of to fractured rock. If you're interested to learn more about the seismic events, there is a lot of that got published relatively recently, but in a nutshell, there are high frequency events and low frequency events. High-frequency events generally are near-surface shallow sources that bounce around the top crust or crust entirely and are giving us properties of the crust. And low-frequency events are more deeper quakes or more distant quakes that then sample the upper mantle or mantle in general. The biggest region for seismic activity was in Cerberus Fossa, which is not unexpected. It's a young tectonic region, and this is also the region where we got our biggest, one of our biggest quakes. And one of the interesting, so this is basically my summary slide. If you're interested to learn more, there's this myriad of science papers that came out halfway through the mission. But the highlights are that the crust on Mars has about 2 to 3 layers, depending on where we are on the globe. That the mantle is pretty thick and unified. It's a single layer with thick lithosphere. And that the core is larger than previously thought. So in a way, there were some nuances, some changes to what we was believed that Mars could have been if it were akin to Earth. So I'll stop there. Thank you very much for the time, and apologies if I ran over time. Okay, I'm getting to the questions online. There was a question about how do we distinguish if the quake is due to impact or any endogenic activity. Hopefully, by listening to the end of the presentation, you could understand the difference. But it is about the frequency domain and the shape of the seismicity. There was a question about whether mass quakes due to impacts would cause boulders to slump down. Yes, but that's all part of the cratering process and would be recorded in that long quake, be buried under that, basically in that long quake signal. I don't think we could distinguish it separately.
We'll just take a quick question from the live audience out here.
Hi, am I audible?
Are you able to hear it? Yep.
Hi, am I audible?
Yes.
Hi, Priyanka here. So first of all, the insights in the insight was quite good. So enjoyed it. I have a question. The last slide shows the data revelation, which is about the seismic activity, and it appears that it is much different from Earth. So can we really conclude that the seismic activity is mostly crustal and there could be no plate tectonics? Is it okay to conclude like that?
I am not a tectonics expert, but yes, that would be my interpretation that it's been long believed that Mars has a single shell planet, so it basically has one tectonic plate, and the tectonic activity that happens within that outer shell, is much milder than what would happen on Earth that has multiple tectonic plates. The largest quake that we got on Mars was magnitude 5, and it was only one of them. Most of them are magnitude 3 and 4, which are actually assigned to the Cerberus Fossa region, which is just a series of faults, nothing major. So it is about the interior structure being different and lithosphere being thicker that would prevent from significant tectonic activity and therefore the multiple plates.
Thank you.
Thank you. So for the sake of time, once again, apologies for the technical glitch initially. So we'll move on to the next speaker, but we are keeping tabs on the questions that are being typed. And so hopefully during one of the discussion sessions, we'll come back. The next speaker is Mr. Binod Srinivasan from the Center for Earth Sciences. Just trying to put our talk up. Is it? Wait. How to share the screen. It is full screen. Wait, I know. Is the screen visible to all the online attendees? I think it should be. Okay, over to you, Binod.
How do you scroll this? Right arrow, is it? 5 minutes, is it? Good morning, and I'll talk about dynamo action in planets and give you some information about the magnetic field of Mars, which was alive once upon a time, but is not, unfortunately, today. So to get a handle right arrow is not working, so I'll have to see. I think it's very slow because of the the Earth is a useful starting point in understanding planetary magnetic fields. And I hope most of you will know that Earth has a north-south dipole-dominated magnetic field. And we expect that any rotating planet will have a north-south dipole-dominated magnetic field. So when did we realize that the magnetic fields of planets actually change in time? They are not permanent magnets. They are actually dynamic magnets. So it happened in the 17th century when the angle between the magnetic north pole and the true north of Earth was found to change in time. So this angle was once upon a time called variation. Now it is called declination. And this was the earliest indication of the possibility that planetary magnetic fields could actually be time varying. And Edmund Halley of our Halley's Comet fame, since then he undertook a voyage of the South Atlantic on his ship called Paramour. He was an avid seafarer too. And he noted that these lines of constant declination actually moved in the westward direction. And this he called the westward drift of the Earth's magnetic field, which now we know to be correct. It's approximately 0.6 to 0.9 degrees per year. And computer models of the dynamo also show that it is true. So explorations were the first that gave us the insight of time-varying magnetic fields. So I was asked to give a brief history of the dynamo before I move on to Mars. So I will tell you something about the early attempts to obtain magnetic fields generated in the laboratory. So Faraday in the 1830s came up with this idea of the disk dynamo, where a metallic disk rotates a high angular velocity in the presence of an existing magnetic field. And the physics students, at least of this audience, should know that the motion of an electric conductor in a magnetic field will give rise to an electromotive force, which is proportional to the cross product of the velocity and the magnetic field itself, which is the V cross B, and that generates an electric current. So if you exploit this property, okay, and connect a lead from the rim of this, take it around and join it again on the axis of this disk, okay, what will happen is the current will be that flows through will induce an additional magnetic field by Ampere's law, which adds on to the existing magnetic field. And this process keeps going on and on. And this new addition was made by Bullard in 1955. And in principle, we could actually detect a tiny increase in the magnetic field due to this process. So now the natural question is, does it go on and on and on till the field becomes infinitely large? But the question is very tempting to ask, but the answer is no. And the reason for that is the electric current that is induced here will interact with the magnetic field to produce another force, which is known as the Lorentz force. And this Lorentz force, as you can see, will try to decelerate this disk, right? And as it tries to decelerate this disk, and this is the saturation mechanism for the dynamo, which prevents the magnetic field from increasing and becoming infinitely large. Now, this was conceptually there for several decades, and it was first realized experimentally, you'll be surprised to see, only in 2022, 23. So the spirit of Faraday is still alive. He's the eternal experimentalist for us. Now, if you take a slight leap of imagination and replace this solid conductor with a fluid conductor, then we can partly explain how the magnetic field in the sun is generated by dynamo action. Okay, and this was done by Larmor in the 1919 meeting of the British Association for the Advancement of Science. And the proceedings of this came out as a 2-page article. That is where we first got to know that we could have a fluid that conducts electricity and generates a dynamo. And it was in the 1940s that people thought of combining the equations of electromagnetism and fluid mechanics to come up with more comprehensive theories of the dynamo. So I will quickly take you through the central equation of dynamo action, where the time variation of the magnetic field is actually powered by convection, which is what feeds the velocity field here, u, and that there's a cross product between the velocity and the magnetic field, which gives rise to this convection term. And this is opposed by diffusion, which comes about as a result of the finite electrical conductivity of the medium. Okay. Now, the ratio of this term to that term determines whether the field of a planet will actually grow or whether it will decay in time. And for Earth, it has been estimated that this ratio of that this first term on the right to the second term on the right is actually 100. Okay? I'll not go to the details of how we get this, but this was the earliest understanding of the dynamo. And these dynamos are typically called kinematic dynamos. And the reason for that is we start off with a field, with a velocity field, and we ask the question whether that velocity field will give rise to the growth of a magnetic field or not. But dynamo theory has evolved since then. And now we know that a dynamo is not as simple as that, because the magnetic field, as it grows, it can also act back on the velocity field. And therefore, a simple equation such as this cannot actually capture the entire dynamo process. Now, what drives convection in a planetary core? There are multiple mechanisms which have been proposed, and the simplest one can be found in our kitchen, where we actually boil water on a hot plate and actually get warm fluid rising and cold fluid sinking. But in a planetary core, this process of convection is strongly affected by the rotation of the planet itself. It changes the way convection looks like. And that also has been studied by Jeffrey Taylor in the 1920s through his important experiments, together with Proudman. And they came up with this idea that the rotation will actually try to suppress velocity gradients in the direction of the rotation axis. And this theorem came to be known as the Taylor-Proudman theorem. And the Taylor-Proudman theorem predicts that convection in the interior of a planet will take the form of columns which are aligned with the rotation axis because of this property of rotation trying to suppress velocity gradients. And here we have blue columns where fluid goes in, and the red columns where the fluid comes out due to the bulk convection that's taking place. And this is the classical mechanism for dynamo action, which was proposed in the 1950s by Eugene Parker. So what he proposed was that there is a differential rotation of a planet, or any astronomical body for that matter, which teases out a north-south poloidal magnetic field to actually produce a toroidal field. And once a toroidal field is produced, we can go back to the earlier process by which we have columnar motion in the interior of a planet, which will actually twist these toroidal flux loops, and they will once again form a poloidal flux loop. So this constant alternating between toroidal and poloidal flux is called the omega alpha cycle, which is a hugely popular model, but it must be kept in mind that this is still a hydrodynamic model in the sense that it simply follows the magnetic induction equation, which I showed in the previous slide. It is a unidirectional process. It is not a coupled process where velocity field and magnetic field are coupled. So this is how state-of-the-art dynamo models look like. This is a weakly rotating model and a strongly rotating model, and we can see the Taylor columns which are produced, which goes back to the 1920s. So again, shows the importance of those kind of discoveries that are still valid now. And we can see that more rapid the planet rotates, the thinner the columns get. Okay? So that is also predictable by the linear theory of Subramanian Chandrasekhar, who worked on this in the 50s. And what do these columns generate? They can generate a large-scale dipole-dominated magnetic field. And stronger the rotation of the planet, the more intense the dipole-dominated field of the planet. Right? So this is quite comforting for a dynamo theorist, because it shows that self-consistent models of the dynamo actually work, because they are able to produce dipolar fields, which is the hallmark of many planets in our solar system. So I'll skip this slide in the interest of time, except to show that this Lorentz force, which I spoke about, must be coupled with the velocity field to actually make sense of the dynamo process, whereas the early dynamos until the 80s was largely determined by this equation only. So how does a magnetic field of a planet evolve from a tiny seed? It's a question that we asked several years ago. And we came to the conclusion that the planet goes through a very chaotic process where the magnetic field is highly multipolar, so there is no preferred polarity of the magnetic field. And eventually it settles to a dipole-dominated state, provided the background rotation is strong enough. And we also came up with an explanation for that. The explanation was that in the early phase of evolution of the planet, the convection is a lot weaker. And so we could actually see that the growth of the field is accompanied by growth of convection itself. And this is something that is entirely missed in the early kinematic models, right? So this can be seen only in a self-consistent dynamo simulation. And this generation of the magnetic field of the dipolar magnetic field has been attributed to the generation of convection that accompanies the early growth of the magnetic field of the planet. Tension remains the same, but the Lorentz force kicks in. And as the Lorentz force kicks in, as the field grows, as the field gradually grows, the Lorentz force kicks in. And then what happens is that the Lorentz force tries to come into an equilibrium with the Coriolis force of the planet. And then what happens is, if you are really interested to know what happens after that, you are welcome to a talk at 4 o'clock tomorrow evening, where I will explain how this works. It's actually spontaneously triggers a class of hydromagnetic waves. And these waves are actually instrumental in producing the dipole field of the planet. And when these waves are suppressed, when the Lorentz force is no longer there, no dipole at all. So this is the lifeblood of the dipole field of a planet. Why do we want to study planetary magnetic fields? I'll go through this next part, just 10 minutes if I have time. It results from motion of the planet's core and the mantle itself. So it's a very useful indicator of the internal movements of a planet. And the reason why we are all here is that Earth has a magnetic field. As you can imagine, it maintains an atmosphere which can support life. And Mars may have had an early magnetic field, which may well have supported microbial life on the planet. So it also gives you useful constraints on planetary structure and dynamics and evolution. So in summary, it's a very useful probe to understand the internal structure and dynamics of a planet, because that is what we can measure on the surface of the planet. So most planets are opaque. So this is one of the proofs. The other one is the seismic data that comes out of earthquakes and so on, and Mars quakes. But magnetic field is a very important diagnostic. It is a probe to probe the internal dynamics of a planet. And coming to Mars, I have only data from the MGS, not from InSight. So I've only spoken to a few people who worked on InSight so far, because I have not renewed my work on Mars since I stopped more than 10 years ago. So the takeaway message for the Martian magnetic field is that tilt and look at the southern hemisphere, we can see that there is a lot of remnant magnetic field in the southern hemisphere of Mars. So strong crustal field, and the southern highlands, they predate 4 billion years. So it indicates an early dynamo. So why this hemispherical dichotomy in the Martian magnetic field? Was there a giant impact in the northern hemisphere that erased the magnetic signature in the north? That seems to broadly correlate with the topographic difference between the southern and the northern hemispheres too. Or was Mars a hemispherical dynamo where core convection was confined only to one half due to this impact? So there are also impact basins in the southern highlands, Hellas and Ajar. They have very little remnant magnetization. So what does that tell? Probably those impact basins formed after the dynamo ceased to operate so that they could not be remagnetized. Yeah. So the dynamo is thought to have ceased to operate within the first few 100 million years of the planet's life, is between 4.5 and 4 billion years. So that 500 million year period, broadly known as the Noachian epoch, before the formation of those impact basins. And several mechanisms have been put forward to the reason why the magnetic field of Mars might have died away. Relatively small size of the planet might have cooled rapidly. So an initially large temperature difference between the core and the mantle might have decayed to a value that is below the critical value for dynamo action to take place in the planet. So this has been proposed as a mechanism. Another competing mechanism is that the core could have been completely frozen out so that no convective motion is possible. However, doubts have been raised after the InSight mission about the existence of the inner core itself. So probably the Mars never had an inner core, and it was always liquid. Even now it is liquid. It's just that it is not convecting strong enough. Okay? So the question of an inner core growing and growing and causing the entire core to be solid might not be relevant after all if the Mars did not have an inner core. The other possibility is that the dynamo is subcritical. What do I mean by subcritical? As the planet cools gradually, its magnetic field becomes weaker and weaker, but convection doesn't die away, even though so there's a weak convection that keeps going on below the threshold of dynamo action. This is the hysteresis, which we see in numerical models also. As we increase the intensity of convection and when we reduce the intensity of convection, the magnetic field is not quite the same. So the magnetic field can be supported by weak convection. And then what happens is there will be tiny perturbations on the core mantle boundary which can extinguish the dynamo. And there could also be a reduction in the average core mantle boundary heat flux following giant meteoritic impacts in the mid-Noachian epoch. So these meteoritic impacts will act as hotspots, several hotspots on the Martian mantle, which can actually suppress convection in the underlying core. And we could also correlate temporally a mantle plume beneath the volcanic region of Tharsis, which is currently near the equator of Mars. There may be a Hawaiian type mantle plume which exists beneath the Tharsis region. And this plume also might not have been stationary. It might have moved in latitude during the Noachian period from, say, 40 degrees south all the way to the equator. How does it move? Because of the motion of the planetary mantle and lithosphere relative to the rotation axis. We can actually have this. So we can actually look at an isolated mantle plume beneath Arcis, which may have contributed to the cessation of the dynamo. So this is a Tharsis bulge from the altimeter of MGS. You can see that the highest peaks of Mars are 12 kilometers here. So this might not have been at the equator, near the equator. It might have migrated to the equator from the southern hemisphere. So this is the kind of model that we have in mind, where there is helical convection going on in the core of the planet, which generates a large-scale magnetic field in the presence of rotation. And what happens is there is a plume that is sitting at a lower latitude, and also a plume that is sitting at the equator, and we can study its effect on convection. And this plume, which is above which there is a Hawaiian type mantle plume, can actually induce a gravity current, which will weaken the helical fluid motion in the planetary core, and thereby cause the cessation of the magnetic field in the dynamo. And this is a model which proposed, probably not hugely popular, I must admit, but neither are the other models for the cessation of the Martian dynamo. So on that note, I will stop and welcome to ask questions.
Oh, it was a very nice talk. Myself, neither from physics or maths background, from geology background. Now, this has a direct relationship to the development of the plumes, right? So somewhere I read that the fluid's Reynolds number has a contribution to the diameter of the convection cell that will happen inside the planet, and a 2-layer, 3-layer convections. So how does this magnetic field and this the dimension of the convection cells, go hand in hand?
Yeah, I don't have an answer for Mars in particular, but for a...
It's for, I'm talking, the data I'm giving is for...
Okay. So our understanding is that whenever there is a rapid rotation of a planet, for Earth it is something like 10 to the -4 radians per second. For Jupiter and Saturn, it's much stronger, right? So the convection rolls are generally thin in those kind of situations. And what limits the smallest thickness of a convection roll is the magnetic diffusivity of the planet. And magnetic diffusivity places a lower bound. So we believe that for Earth, the typical size of a convection roll is something like 10 kilometers and above. So 20 or 30 kilometers is not unthinkable, but something like 5 kilometers is very unlikely. What happens is that if the size of the convection roll is, say, very small, it will not be able to support not the hydrodynamic Reynolds number, but the magnetic Reynolds number that is necessary to keep the magnetic field going. So that magnetic Reynolds number should be at least 10 for the dynamo action to take place. So that is probably more important diagnostic for the dynamo action in a planet than the hydrodynamic Reynolds number itself. The reason for that is the magnetic diffusivity is the controlling diffusivity in a magnetic core. It is not the viscosity. It is not the viscosity. It is the magnetic diffusivity, right? So the magnetic diffusivity is what limits the smallest cell, convection cell that can exist. And that will also, if there are smaller cells than that, the field will not be supported. So, but the height of the cell can be the height of the core itself. For example, it will be of order 1,000 kilometers, but the radius will be not more than a few tens of kilometers.
Hi, Binod.
Hi.
For that. Is there anything distinctive about the pattern of the remnant magnetic field in the southern hemisphere? It's kind of that blobby, sort of linear pattern. Is there anything that's distinctive about that?
They are mixed in polarity. So people have asked the question if a magnetic field was generated only in the south. It was never generated in the north, but it could well be that it was dipolar and the signature in the north was wiped out. In the south itself, there is no indication that the field is of one sign only. We do get both polarities, both north and south pointing remnant magnetic fields in the south. So it is a bit scrambled. So it is difficult to tell if this scrambled signature is partly due to the bombardments which might have scooped out a more coherent one-signed pattern. For example, Hellas, for example, doesn't have any field at all. It might have removed some signature of the magnetic field which existed there. But yes, we don't have any coherent large-scale south-pointing or north-pointing field in the south. It is a mixture. So I cannot explain that, but I would still like to think that the Martian magnetic field was still largely dipolar, and gradually it got, the signature got eroded for various reasons in the north and the south, and it never recovered after that. So the scrambled signature probably persisted. But I think, yeah, it's not an easy question to answer that question.
We have any more questions from the audience here? Yeah.
Hi, thank you for the amazing talk. I think this is a question not just for you, but for the experts in the audience. And we know that magnetic field is essential for life to survive in any planetary body. So, and exoplanets have always been studied regarding what kind of atmospheric compositions are present, etc., etc. We do not know whether it's a thin atmosphere or a thick atmosphere, and pretty much the magnetic field would decide that. Do we know? It's a general question for the audience. Do we know if there are, telescopic observations or methods to actually identify whether an exoplanet beyond the solar system, of course, has a magnetic field or not? It's sorry. Thought on. Next slide. And the planet to expect, and the solar wind interaction also. The solar wind interaction with the planet also gives you signatures of possible magnetic fields. That's the way for exoplanets now. But
figure that out. The characteristics of the planet will be such that it's completely flat. The bottom from the surface to the bottom rather than from the bottom to the top.
Yeah.
And there are those series of papers by Indiana, Valencia, and Rico Connell that try to look at whether exoplanets can have spatial connections. But the goal that if they aren't in so-called goal is not known and we can't support the failure in that. But I'm not aware of anything that take it from getting to.
We know that for Earth, say 3 billion years ago, people argue. There was a science paper which came at least 10 years ago that the Earth's magnetic field was only half as strong as it is today, and the magnetopause was much closer than it is today. and it may well have stripped off a lot of water from the Earth's surface those periods. So yeah, so the intensity of the field does have an important role in determining the atmosphere of a planet and whether there can be water on the surface of the planet.
Yeah, Vinod, maybe you can revive your work for exoplanets now that there are 6,000 such samples out there.
I don't know where to begin there.
We don't have to go outside the solar system. Mercury has active magnetic field.
Yes, Mercury has a magnetic field. It's also dipole dominated. It's about 1,000 times weaker than at least it's in the nanotesla range. It is much weaker than the Earth's magnetic field. And the weakness of the Mercury's magnetic field is attributed to the fact that the core might be highly stratified. And so dynamo action takes place only in a part of the core. And that has been proposed as the main reason why Mercury's magnetic field is a few hundred nanoteslas, as opposed to Earth's field, which is at least 1,000 times higher.
Is there anything that a mission to Mars could help clear up in terms of these questions that you brought forward?
Yes, we could definitely measure the magnetic field intensity to a greater accuracy in the southern hemisphere. And also the fact of whether inner core is completely ruled out in Mars. I think we need a final answer to that. And then when I visited some of these scientists who worked on the InSight mission, they were sitting on the fence on this matter. And if the inner core does not exist, I think the dynamo models will completely change. And the window in which you actually get a dipole will be considerably shortened compared to when there is a inner core, right? So it's not that the magnetic field will not be dipolar, but the range of dipole action will be considerably smaller than what it would be if the inner core existed. So we would definitely like to know from the seismic data, which seem to point out that the Martian inner core may not be there and the core would be entirely liquid, which I think the talk before me tried to suggest. I don't know how conclusive that discovery is. So we would definitely like to know more about from the seismics about where the core begins, that is to say where the mantle ends, and so that we can accurately feed these dynamo models and see whether the results of these dynamo models is actually dipolar or not. That can, because most of the models we have now produce dipole dominated fields, so which is not there, at least in the remnant signature of on Mars.
Right. I think for the sake of time, we will possibly just take a quick 15-minute break. We are running about 17 minutes behind schedule. So I'll inform the next two speakers are both online. So I've informed them that we are running late. So there's coffee outside, and we can continue the discussion also.
Got it. Very interesting. We did a Mars analog last year. They have more idea about a Mars analog last year.
Arunavu, are you able to listen to me?
Hello.
Hi, Arunavu.
Yes, now my voice
Yeah,
is
you're
right.
audible perfectly. Can you speak like few sentences?
So I'm audible right now, right?
Yeah, you are perfectly audible. Okay, perfect. Sound check completed. Thank you.
Okay.
Can I share my slides? This is Amit from ERM. Hello.
Yeah, you can share it right now.
Yeah.
Yeah, you can share your slides.
Just a minute. Is it appearing?
It's visible, yes.
I have made it full screen mode. Please check.
All right, welcome back, everyone. So the next couple of presentations have a slightly different flavor. They will tell us more about understanding Mars from a Martian meteorite perspective. So the first speaker is Dr. Amit Sarbadikari from Seattle, and after that we will have Dr. Debashish Upadhyay from IIT Kharagpur. There's a third speaker who was supposed to speak, Dr. Nachiketa Rai, but there's some emergency for which he cannot speak today. So we're trying to schedule his talk tomorrow, okay? I will turn off my microphone, and Amit, you can take over in 5 seconds.
Am I audible? And my slides are visible to online audience and the auditorium? Hello. Hello.
Online, yes, I can vouch for it, but
yeah. Should I start?
Amit, you can start. Can you hear me?
Okay, okay, thank you. Yeah. Okay, so thanks to the organizers for giving me the opportunity to present this lecture at the Mars workshop. So in recent decades, Mars exploration missions, including landers, rovers, and orbiters, and many, and more importantly, Martian meteorites, have provided valuable insights into the chemical and mineralogical properties of the Martian surface. Here, I will try to provide some glimpses to make this diverse audience aware of what type of information we can retrieve about the red planet. So this image, this cover image indicates bulk of rocks on the surface of Mars look similar to this right side brecciated meteorite. This is one famous Black Beauty meteorite, NWA 7034, and a few other of its pairs. So, in second slide here, like other terrestrial planets, Mars has been differentiated into core, mantle, and crust. And InSight mission is giving data to understand the internal structure, as you have seen from previous speakers. And they have concluded that Mars has not cooled to a completely solid iron core. Rather, its interior is made up of either completely liquid iron core or liquid outer core with a solid inner core. But that is very small solid inner core. So now this slide shows that interconnected aspects of planetary science. Many points to discuss here, but in brief, Earth is dynamic because interior as well as external processes is active and still ongoing. And throughout the geologic evolution, it has been active. Had its active interior process in the past and which ceased over the time. And we want to know those processes as Martian scientists. So, and the reason is we also want to know the past of our own planet, Earth, because older record erased since Earth is still dynamic. So to start with the evolution of the Martian surface and interior, as I mentioned that Mars was active at the early stage. So you can see at the leftmost side that, let me use the pointer, the magnetic field was active, very early stage, large impacts, volcanism, aqueous environment, all are very much active at the early stage. And gradually the activities got went. And now how we know about these processes? Basically, we can study the surface. Surface means its minerals, its elemental composition, and it shows that the early stage of very aqueous environment, and that gradually converted to very dry planet surface of the Mars. So now let me discuss about the primary composition or the igneous composition of this planet. This map made by Tanaka et al. 2014 has been modified, and this shows that the early Noachian, mid Noachian, or late Noachian, even Hesperian, Amazonian, they are all covered by basaltic rock composition. And if you see that they early, Noachian to Hesperian, they covered the most of the area. Okay. And Amazonian is 3 billion years, more than 3 billion years, 3.2. So the crust formation was very early, and it retained because Mars lost its plate tectonism. So whatever happened at the early stage, and the record has been fossilized in the surface or subsurface. But is it so? Is the composition is all basaltic? Yes, they are basaltic, but our study shows that there are compositional trend from Noachian to Amazonian. The surface composition shows some complex processes, due to the trend, geochemical trend, and this happened due to the interior processes like mantle melting and the interaction through which it has gone through during the crystallization at the surface. So different element to element plot shows this trend, not going into details, but in the nutshell, this shows the compositional differences that has been observed in different provinces. We have mentioned different provinces based on their time of formation, starting from Noachian to Amazonian. Okay, so if we want to see the planetary mission, then we'll always observe this type of trend, that orbiter, theta, then lander rover, and then finally comes to the in situ either manned mission and sample return mission. So why this trend? because we'd like to know in details of these processes. So we need to study them either in situ on the surface of that planet, in this case Mars, and finally would like to understand them or study them in our lab, in our state-of-the-art labs. So that's why, although we start from reconnaissance orbiter study, but gradually we narrow down our area of interest, but that it is not narrowed down as such. It is to get the broader aspect of understanding the planet evolution. So Mars missions are driven by the investigation of past climate, its geology, role of water, and the timing of those processes, explore resources if anything is there, and of course microbial life and the habitability. So to understand all these things, we need detailed observation or detailed study. And for that, we, as I mentioned, we continue these in situ observations. Here, one curiosity observation has shown us the variation in the rock composition on the surface of Mars, at the, specifically at the Gale crater, and it shows that there are alkaline rocks which are sodium-potassium rich and which are very much common at the ancient terrains than the younger terrains. This suggests some kind of global magmatism was there. And this type of rock has not been previously observed, but this is the in situ rover observation that they have found some very highly alkaline rocks in Gale crater. And these rocks found in the interior of Mars, maybe 5 miles below. And the magma moved up through cooler rocks under a higher fraction of dissolved water. Higher fraction of dissolved water means when it is coming from deeper, they have the higher concentration of water content. And they are highly fractionated, as I mentioned. And generally that happens in case of our Earth, if we see, that is generally occur in the island chains. So that means kind of rift zone or plate tectonism was involved. But we cannot say that Mars had a plate tectonism. So these are the questions, unanswered questions that we have to find, and works are going on to understand these different sample analysis, in situ data analysis, to understand why the alkaline rocks are so prevalent in the Noachian time. Then coming to Martian meteorites, which I've been talking more. Martian meteorites are, there are around 400 Martian meteorites that formed on the Mars. And in absence of the return samples, they are the only samples available to study in our labs. And they are ejected from Mars by an impact event and finally traversed interplanetary space before landing on the surface of Earth. So our primary source of understanding about Mars is the composition, age, formation, evolution, impact, and alteration processes all have been given by this study of the Martian meteorites. So how? I will just show here some highlights of what we are studying in our labs. This is one famous Martian meteorite is sent, and this is being studied some time back, and we studied the chemical composition, mineralogical composition, the rock types, trace element study, isotope study, and then we come to know that this type of rock has formed in a region which is very depleted in trace element content, but it has come up through some process where it has been contaminated at the upper mantle, and then it has come up, and by meteoritic impact, it has ejected from the surface and we have studied this. So this left-hand side of this slide shows their evolutionary trend. It started from melts, then it passes through olivine, spinel field, and finally at the surface, this is almost adiabatic rise, and then at the surface, it formed olivine, pyroxene, spinel, different type of pyroxene and spinel, and plagioclase, of course. So indicates the interior environment, interior processes, and more importantly, we have found there are residual melt pockets which are enriched in trace element or large rare elements, Nile elements, which incorporated during the ascent of the magma, and that has enriched to some extent to some part of this meteorite. Similarly, we have studied another type of Martian meteorite, which is not found at the surface, but it is a kind of cumulate rock which formed at the deep beneath in the magma chamber. So this type of study is important to understand better than the basaltic rocks, because basaltic rocks you have to trace back a lot of processes or calculate back a lot of processes to understand what has happened at the interior. But when you have a sample which is already crystallized at the depth, and then some processes, external processes like impact, it has got exposed, then you readily understand the processes involved in the, especially at the magma chamber. So studying the strontium and neodymium isotope systematic and trace element and melt inclusions, we have found that there is a connection gap in the Martian mantle which has not been told earlier. There is chemical layering in the depleted mantle, and there are processes which involved in enriching the material which is not supposed to have enriched as such. See, Mars has not plate tectonism, at least at Amazonian time, right? So it should not be enriched like what we see in case of Earth's mantle processes. But we see this process, there are some enrichment. We studied some potassium-rich glasses and other phases, which indicates that there are enrichment happened in the process of its ascent. So another thing to touch here that there are, I talked about primary rocks. There are secondary rocks. I mean, the Mars surface is sediments. There are lots of sediments. So this is a view of secondary rocks and minerals on Martian surface taken by NASA's instruments. The strata indicate the ancient depression and existed before larger bulk of the mountain form in this figure. Then the preservation of some alien dune here in this figure, and the dune stratigraphy is preserved. There are several types of sedimentary rocks. They are dark gray boulder, cobble, reddish markstone. Here all are given in this picture. There are conglomerates, pebbles, etc. And this one indicates north polar layer deposits rich in water ice. They may be several miles thick, and it may be remnant of a buried impact crater now being exhumed. So North Pole, you know, they are deposits, ice deposits accumulated. So these buried craters are generally inaccessible, but in few locations we can see this through erosion, they are visible. Now also here we can see the rock cycles and sediment cycles on Mars. They are, Martian rock cycles include igneous sedimentary metamorphic rocks, and impact events contribute to production of clastic debris, melt, shock metamorphic products. And the Martian sedimentary cycle, this includes rock exposure, rock breakdown, trust, production, etc. And so we are also working on the secondary samples like serpentinization. Serpentinization, you can observe that these dots indicate some serpentine deposits on the Martian surface. And serpentinization is important. It's a fundamental planetary process that promotes habitability by generating hydrogen-rich fluids and through some hydrolytic alteration. So this enables carbon reduction and abiotic organic synthesis. So on Mars, orbital detection of the serpentine minerals indicate past liquid water interactions. And this compositional control govern Martian serpentinization, but it remains poorly constrained. So this global distribution of serpentine on Mars is observed. So in the process of to understand the serpentinization process, because we do not have any return sample or even Martian meteorites to give some widespread occurrence of serpentine, so we have to consider some analog sample. Sri Lanka has a wide extensive deposit of serpentines. We collected a lot of serpentine samples and the study is going on. A preliminary result has been published also. So we can discuss these things later because this is ongoing work. And finally, we would like to touch on this, that halogens are very important. Sorry, turned off. Hello. Hello.
Yeah, hi, you are audible.
Yeah. Okay. Right.
Yeah, you can go ahead.
So, yeah. So halogen cycles in soil and sedimentary rocks are relevant to observe the atmospheric cycles. So with this, I end and I can take questions. I think I am in time.
Hi, Amit. Thanks for your talk. We'll invite some questions now. Okay, maybe any questions on it, or maybe some question online? Let's take a look. Maybe there are no questions. Oh, yeah, Shama has a question here.
Amit,
yes.
You have studied both meteorites and from remote sensing data. Has there also been attempts to put them in context, and how successful are we in that?
Yes, of course. And we studied the meteorite samples to understand the primary compositions on the surface, which we observed from the orbit. But we'd like to understand more details of how they have formed and evolved. Because we would like to understand the interior processes, because you have to understand that interior processes that governs everywhere. I mean, its surface, atmosphere, hydrosphere, everything is governed. Of course, there are external processes like impact events, but interior processes are the most important. So when we see basaltic surface on the surface from orbiter, and we see the differences, the next question should be that how these differences are coming. Are they? I mean, if there is no plate tectonism, if there is no mantle interior processes, then we would expect that everywhere composition is same. Okay, or uniform, but we don't see that. So that is the question, that whether or how the differences are coming and what are the processes in that.
Okay, thanks, Amit. I just, this is not a question related to your talk, but in the previous presentation that was on, initiation of, a magnetic field or a dynamo, are you aware of the studies by Benjamin Weiss on Martian meteorites and their magnetic field? This is just because you work on Martian meteorites. If not, we can talk about this later, but that could actually add to the discussion from the previous talk also.
Yeah, I know that.
I think there were some studies by Benjamin Weiss at MIT who actually studied, he's a paleomag guy, but he worked on Martian meteorites. So I cannot remember it at this stage. But anyway, so thanks a lot, Amit. We will move on to the next presentation, and we are trying to collate all the questions that are being typed up. So for the online audience, if you have questions, please type it. We will try to collate all of them and find answers for them during discussion sessions. Okay. So Amit, could you unshare your slide? Thanks again.
I have unshared.
Yeah, it's unshared. Thanks. Yeah. So next presentation is going to be by Professor Devashish Upadhyay from IIT Kharagpur. Devashish is already online. I can see him. Devashish, if you could share your screen.
Okay. Thank you.
Yeah, you're audible.
So is my screen shared?
Yeah, it's shared. Just go to the full screen version and then I'll turn off my mic. Thanks. Yeah, it's visible.
Yeah, okay. So thank you everyone, and I think it's still, just turned afternoon. A very good afternoon to all of you. So just let me know if the slides do not move, because I am unable to see your screen in the auditoriums. So I'm an isotope geochemist, and today I'll talk about the formation and early evolution of Mars as we understand from radiogenic isotope systems. So now we have seen in the previous talks that there have been discussions on different events happening in Mars. So formation of the mantle, crust, alteration, water, etc. So we are all very much interested in knowing when things may have happened. So, for example, if you look at the size of Mars, you clearly see that Mars is much, much smaller than Earth or Venus. In fact, there have been suggestions. So that's a problem for planet accretion models, that the size of Mars is difficult to explain, the small size of Mars. So some people suggest that it just got kind of frozen at the planetary embryo stage, and unlike Earth and Venus, which evolved into completely differentiated planets. So the question then is, how is the evolution of Mars similar or different from that of Earth in terms of the events that happened early on? So I'll mostly be talking about the events that happened early on. So that means the formation, accretion of Mars, its differentiation into the core mantle crustal structure that it currently has. And radiogenic isotopes help us in this respect because they can give us the absolute and the relative timing of events. And you can use the isotopic compositions as kind of to fingerprint the source regions to characterize the different reservoirs. So, as I said, on today's talk, I'll mostly focus on the early differentiation history of Mars and the nature or the kind of mantle crustal reservoirs that may be there as we infer from radiogenic isotopes. Now, of course, all radiogenic isotope works are essentially dependent on Martian meteorite samples. So the Martian meteorite samples are mainly divided into three major groups. They are called the SNC group of meteorites, so shagotites, knucklites, sachignites. Shagotites are mainly basaltic, okay, so like basalts on Earth, similar compositions in a way. Whereas knucklites, sachignites, I'm being very general, not getting into specifics of things. They are more like mineralogically and compositionally rocks similar to that we have in the Earth's mantle. So dominated, we call them ultramafic rocks. So These three groups, they're actually quite young. And just to give you a small bit of information, that the Shergotite group of meteorites is named after a meteorite called Shergoti, which actually fell in Bihar in 1800 something, and in a place called Sherghati. And since the British could not pronounce Sherghati, they made it Shergoti. So the SNC group of meteorites, that means the Shergotites, Knucklites, Shashignites, they're all relatively young. So we'll just talk about their ages a little later. But of course, there are also ancient meteorites on Mars. For example, we have the orthoperoxenite Allen Hill 84001, the much older. And then you have the Northwest Africa 7034, also called Black Beauty, which Amit just talked about. So it's a regolith breccia, which contains very old components in there. And the bottom line is that meteorites are our main window to understanding of the interior evolution of Mars. Still, of course, we have samples coming back. So, and a little more background on the kind of radiogenic isotope systematics or toolkits that we use to study Martian meteorites. So we divide them into short-lived systems. Short-lived systems are those which have very small half-lives. So for geologists, like half-lives on timescales of million years is short half-life. So these are all extinct. They're also called extinct isotope systems. For example, the decay of 182 hafnium to 182 tungsten, half-life of about 9 million years. And the decay of 146 samarium to 142 neodymium. Again, this is a half-life of about 103 million years. The point is, these are short-lived systems or extinct systems in the sense that they were only active within the first few million years or first few 100 million years of the formation of the planet. So after that, all the parents decayed away, and therefore we do not expect the traces of their decay to form later than about 50 or a few 100 million years. So how these work is, suppose you have a planet, say for example the hafnium tungsten system, where 182 hafnium decays to 182 tungsten. There is a beta minus decay. Now 182 hafnium is a highly lithophile element, so it partitions into, say, the mantle of a planet, whereas 182 tungsten is a highly siderophile element, so it will partition into the core. So you can use the fractionation of 182 182 tungsten to constrain the timing of core formation in planetary bodies. For example, if you have an undifferentiated planetesimal or a planet or a planetary embryo, and if you have separation of metal into a core and the remaining silicate into a mantle, so during this separation process, tungsten will go primarily into the core, where hafnium goes into the mantle. So the core evolves with a very low or almost zero parent by daughter ratio, whereas the mantle would evolve with a very high parent by daughter ratio comparatively. So and this is reflected in the tungsten isotopic composition, expressed as here as epsilon 182 tungsten. So the core has very unradiogenic tungsten isotopic composition, which remains more or less constant with time, whereas in the mantle you generate lots of radiogenic 182 from the decay of 182 hafnium. And therefore it has radiogenic tungsten 182 isotopic composition. Of course, this is true only if the differentiation or the fractionation of hafnium from tungsten happens within a few half-lives. That means within in this case for the hafnium tungsten system, within 50, 100 million years of the formation of the planet. Similarly, you have the samarium neodymium, the short-lived system, where both samarium and neodymium are lithophile elements, so that means they partition into silicate phases, and they get fractionated during large-scale mantle differentiation events. So again, this is a short half-life. That means they record mantle differentiation events that happen very early on in the planetary history. So for example, if you have a mantle differentiation event just after formation of a planetary body, so you generate reservoirs with high parent by daughter ratio, so we call them depleted reservoirs. So they evolve with time to produce more radiogenic compositions, whereas you have other reservoirs with low parent daughter ratios, we call them enriched reservoirs, that evolve to less radiogenic compositions. So in addition to these short-lived systems, which are extremely useful for understanding early planetary processes, of course, we also have several long-lived isotope systems that I have listed here. So rubidium, strontium, samarium, neodymium, lutetium, hafnium, decay, uranium, lead, rhenium, osmium, etc. These are all used to track different mantle processes, characterize the timing of formation of these reservoirs, how they interact, and so on. So with this little background, now let's look at some of the data that we have on Martian meteorites. So these images that I'm showing here, they give you the ages of the Martian meteorites, and from which we can find out the time scales of the Martian magnetism. We'll see that most of the shergottites are very young. So they all have ages roughly between 165 to 187 MA. Some are a little older. So there are different types of shergottites. I will talk about them a little later, but by and large, they are all very young, less than 574 million years. The knucklites and the sachignites, which possibly are samples from the Martian mantle, they are a little older. So they have crystallization ages of about 1271 to 1419 million years. And the cosmic ray exposure ages of about 11 to 12 million years. So this essentially tells you the travel time from Mars to Earth after ejection from the planet. So the interesting thing is that the SNC meteorites, all these meteorites, they're all quite young. But of course, there are some ancient ones also. For example, Allen 84001. This has been dated at 4.1 GA using lutetium hafnium system. And then you have zircons in some clasts of the regolith Brescia, Northwest Africa 7034. And those zircons have been dated to 4.48 GA using the uranium-lead system. So which indicates now on Earth, zircons crystallize in felsic or granite-like rocks or magma. So which indicates that there was definitely some early felsic or granitic crust-like material that formed within the first 100 million years of the formation of Earth. Now, the interesting thing is that most of the Martian meteorites are very young, so as you can see, whereas the Martian surface appears to be extremely old. So people think that most of the surface could be older than 3GA. So which suggests that most of these meteorites are possibly sampling some very localized young reservoirs. The other interesting thing is that although these meteorites are young, if you look at some of their isotopic signatures that I will talk about a little later, we see that these isotopic signatures were developed or generated very early on, just immediately when the planet formed. So they retain isotopic signatures or anomalies, which indicates that ultimately the reservoirs that they were derived from, they're very ancient reservoirs established during the early history of Mars. So we can use the hafnium tungsten short-lived system to date core formation on Mars. So I'm just showing you some images and the results of several studies where people have integrated models of planetary accretion with those of metal silicate partitioning and hafnium tungsten isotopic evolution to show that the material from which Mars was built, so it's supposed to be a non-carbonaceous chondrite kind of material. So they had oxygen fugacities of about 1.3 to 1.6 log units below the iron rustite buffer. So quite reduced material. And these simulations suggest that Mars accreted most of its mass within 5 to 15 million years. And that the core formation happened within a very short time, so within 5 to 10 million years. And the Martian mantle, it turns out to be, is highly depleted in highly siderophile elements like platinum, rhenium, osmium, etc. So these are refractory siderophile elements. So the only way in which you can deplete the mantle in them is if you fractionate or partition them out into the core. So which suggests that the core formation process in Mars was very efficient. because that it led to very efficient metal silicate separation. So very early core formation within a few million years, within 5 to 10 million years on Mars. Now, what people also did was they measured the variations in 182 tungsten, so which I just explained that this is produced from the decay of 182 hafnium. This must have happened within 50 million years of the formation of Mars. And the variations in 142 neodymium, which is produced from the decay of 146 samarium, again must have happened within the first 200-300 million years of the formation of Mars. And recent data suggests that so those samples which have very radiogenic 182 tungsten also have radiogenic 182 signatures and vice versa. So, and these are data from a large number of meteorites now. So there is a correlated variation of the tungsten isotopic anomalies or compositions and the neodymium isotopic, 142 neodymium isotopic compositions. And this can only be explained through a process of global differentiation of the Martian mantle, because the silicate differentiation of the Martian mantle is the only process where you can fractionate both samarium from neodymium for the ND system and hafnium from tungsten. So it is believed that Mars very early on underwent large-scale planetary melting, so it's called a magma ocean stage. And when this magma ocean crystallized, so it crystallized within about 20 to 25 million years after the formation of the solar system. So the early on in the crystallization stage, you form a core, okay, iron-rich core, and then you crystallize the magma ocean to form the mantle within about 20-25 million years. And in the next 15 years or so, from modeling, etc., people have shown that you form all the whatever crustal reservoirs are there. So in summary, so Mars definitely had some sort of a magma ocean, which ultimately crystallized into a basaltic crust and a layered mantle. And the reservoirs that we see on Mars, the mantle reservoirs, crustal, even the early atmosphere that was there, they were all established within 20 to 40 million years of the formation of the planet. So we can also use long-lived radiogenic isotope systems to characterize the nature of the mantle reservoirs or crustal reservoirs that we have on Mars. So these are just some representative plots showing neodymium, strontium, isotopic composition of some Martian meteorites, essentially the SNC meteorites. We see that you can divide the shergotite group into 3 different types. So one type is called the depleted shergotites, which has very more radiogenic 142 and 143 neodymium isotopic compositions, whereas the other group is called enriched shergotites, which are very unradiogenic isotopic compositions. So the depleted shergotites are derived from a source that had low rubidium by strontium ratio, high samarium by neodymium ratio, high lutetium by hafnium ratios, whereas the enriched shergotites have complementary trace element and isotopic signatures. Now, interestingly, all these 3, and you have the intermediate shergotites having compositions in between. They all plot on an isochron, which gives a slope of about 4.5 billion years. So that means although these meteorites are young, so most of them are younger than 200 million years, although they are very young, they are ultimately derived from sources that were established long time back at about 4.5 billion years. So the mantle sources of these meteorites, ultimately, they are very ancient. So somehow you produce these ancient reservoirs, and then these reservoirs appear to have got frozen in time till you had the volcanic activity that produced the source rock of these meteorites. So the knucklites and sachignites, in contrast, they have very different isotopic compositions, and people argue, I'm not going to the details, that this is because of the more complicated evolutionary history of the parent rocks of these meteorites. So We also see something similar when people measure the lead isotopic compositions, that you can define 3 different groups: depleted, intermediate, enriched. So depleted means would be similar to our upper mantle, where enriched would be more crust-like compositions. So you can see clustering of the lead isotopic data, where the depleted ones have very unradiogenic lead isotopic compositions. The enriched ones have very radiogenic compositions. And these reservoirs, again, appear to have been established very early on. So you can think of a very early Martian mantle at 4.5 GA. And then this differentiated into reservoirs having different uranium by lead ratios. And these reservoirs have evolved with different mu values. So mu here is the uranium by lead ratio. So you can see these reservoirs, this reservoir, the enriched ones require high uranium by lead ratio, whereas the depleted ones require low uranium by lead ratios. So the lead isotopes also tell us that you formed reservoirs very early on, and they largely remain closed with very little addition of any radiogenic material till recent times, when these reservoirs melted to produce the source rock of the young meteorites. Now, and finally, one more slide where I talk about the highly siderophile element content. So highly siderophile elements are elements belonging to the platinum group elements. They are important because they tell us about how efficient the core formation process was, and whether any later material has been added to the mantle after the formation of the core. Now, so what appears is that the Martian mantle is highly depleted in siderophile elements, even significantly depleted than the Earth's mantle. So this has led people to suggest that there was a very efficient early core segregation. And secondly, that there was very little addition of material from, say, meteorites, etc., during what is called the late accretion. So the estimate is that for Mars, the kind of mass added during late accretion was about 0.25 the mass of Moon, whereas in case of Earth, it was significantly higher, roughly about 0.5 times the, or 0.58% of the mass of the Earth. Now, rhenium osmium isotopes, again, they show similar behavior as the strontium neodymium system, in the sense that they give ages, isochron ages, that are similar to what we get from neodymium and hafnium. And again, the data here clustered into groups corresponding to the depleted, enriched, and the intermediate chagotites. So all these isotope systems, they clearly support an efficient early core formation and establishment of old multiple mantle reservoirs that formed very early on. So estimates that may have formed already by 4.5 billion years. So, of course, this cartoon shows you the kind of course, this imaginative, that the kind of structure, crust mantle structure that may exist on Mars, where you have the formation of a magma ocean on Mars. And when this magma ocean cooled and crystallized, so you initially produced a deeper layer, which was depleted in incompatible trace elements. So there's the lower mantle accumulates. And then you have later differentiates of the magma ocean, which are more enriched in incompatible trace elements. So this upper mantle accumulates. And then you have a reservoir, which is called a depleted mantle reservoir, possibly because that is the reservoir from which the ancient basaltic crust was extracted. And all these reservoirs, they were produced very early on, and they have been tapped, of course, at different depths and at different times, reflected in the composition of the meteorites that we have today. So finally, I'd like to point out that we can also use radiogenic isotope systems to, in fact, see if there was water, if there was weathering, very early weathering, and if there was hydrochromal alteration. And just one or two examples. So people have measured the strontium isotopic composition of, carbonate-rich fractions from the orthoperoxenite alanine 84001. And they find that the carbonates together with other phases, they find a very nice isochron age, which gives an age of about 3.95 billion years. So carbonates found very early on, and all these carbonates, as well as the other phases, they have extremely radiogenic strontium isotopic composition, very high 87/86 ratios that could only have been produced from the decay of very rubidium-rich phases. So people have suggested that this kind of high 87/86 ratios could only have been produced by fluid-induced alteration of phyllosilicates, micaceous minerals, because micaceous minerals are rich in rubidium, the parent isotopes. So, and these must have been produced before 3.9 GA. So already you had phyllosilicates being produced prior to, say, 4 GA. So, and these have been argued to as evidence for wet clay-rich conditions on the surface of Mars very early on. Then, in another example where people have studied, this is a very unique meteorite, the Martian regolith breccia, Northwest Africa 7034, also called Black Beauty. So, where in different class, people have found evidence for hematite, goethite, etc. So, which indicates evidence of past hydrothermal activity. And in some clasts, people analyze zircon using uranium-lead system, and these give ages of about 4.43 billion years. So some of these, so zircons form in felsic rock, so clearly there was definitely some continental crust of felsic material that formed very early on. And many of these apatites and altered zircons, they give intercept ages of 1.5 GA, which have been interpreted to reflect some sort of a thermal overprint that the regoliths components have experienced. So we can use radiogenic isotopes in this perspective as well. So in summary, if we synthesize all this, we can see that, you know, Mars, from hafnium tungsten system, isotope system, we see that it accreted very rapidly and core formation happened within about 10 million years. This was followed by differentiation of Martian magma ocean, which we constrained from samarium, neodymium, hafnium tungsten isotope system. Crust formation continued for another few million years, 10, 15 million years. And all during these stages, of course, you had magmatic activity, which led to degassing and formation of the early atmosphere. So a lot of this understanding, so clearly from the isotope systematics, tells us that Mars is was differentiated planet, and it developed a heterogeneous multi-reservoir mantle very early on during its differentiation. So I'd like to end by posing some outstanding questions that we still need to answer. For example, some of the isotopic signatures that we see, whether they are primordial heterogeneity or there was some form of crustal recycling early on, and provided, of course, there was some sort of planetary tectonics operating. Then are these only mantle reservoirs that we know of? So are there more reservoirs? What are their depths, spatial extents? And we have very little idea on the geodynamics of the Martian mantle, in the sense that whether we had stagnant plate or maybe some form of nascent plate tectonics operating early on, which got frozen in time. So these are some of the questions that we can look forward to, and hopefully, you know, some sample coming back from Mars would be very helpful, as they can help us to pinpoint specific locations where they're derived from, and which will help us to build up a better picture of what the Martian surface and subsurface looks like. Thank you.
Thanks, Debashish. We have, are there any questions from the in-person audience? So I'll just check that.
Hi, sir.
Yeah, thank you for the talk. So I wanted to ask that the samples that we are collecting from Mars, how do you know those are primordial or there have been involvement of some remelting or any other crustal activities? And secondly, if it's collected throughout the planet, like for Earth, we can get a work silicate Earth composition from all around the planet. So the meteorite sample that we are collecting, is it giving us an overall average idea?
Okay, so you have multiple questions in there. So first thing is that, of course, most of the Martian meteorites I think that we have are finds, so they have been lying on the surface. So what that may lead to is some sort of terrestrial alteration, weathering and alteration. So when people study these meteorites, they try to take care of those effects. So bulk of them are not find. Find means when you actually run after the meteor and see where it falls and immediately collect the pieces. So unfortunately, most of them are false. So some could be affected by terrestrial alteration, but not melting. Melting happens as the meteor travels through the atmosphere. So because there is lots of friction and there is frictional melting, it generate a crust, melting crust on top of it. So when people study, they get rid of this this crust on top. So that to expose the more pristine material in the interior. So when we do this kind of studies, so some of these are things are taken care of, and also people do some leaching studies to get rid of terrestrial alteration effects, etc.
Thanks. Hi, sir. This is Shubham from. I have a question. Can we infer the basic stratigraphy from the meteorites that we have from Mars?
No, we can't. So what I showed you is, kind of a conceptualization that people think may exist, but we have absolutely no idea. So this is this stratigraphy. What people talk about is essentially based on, since this is a kind of a primordial stratigraphy established during the crystallization of the Martian magma ocean. So people do thermodynamic calculations and see what kind of phases would crystallize from the magma ocean at specific depths and compositions, etc. So based on that, so we have ideas of the kind of minerals that would form and the kind of layering that would develop in the mantle. So these kind of things have also been done for, say, Earth, for example.
But if you had a magma ocean, where are the anorthosites or the creep phase? We don't see that prominent anorthositic rocks as has been observed on the moon. So where are those?
It's when you crystallize a magma ocean, not necessary to have anorthosites forming always. So because most of the minerals that would crystallize early. Pardon, somebody said something?
You can continue, Ashish. We are able to hear you.
Okay. So you need not necessarily have anorthosites like you have on the Mars. And in fact, some of the isotopic signatures, I've not gone into details of it. So people argue that they could essentially be mixtures of, early formed cumulate from the ocean and late stage residual liquids, more like creep kind of liquids. But of course, you do not see compositions very similar to creep from the Martian meteorites, possibly because most of the Martian meteorites are basalts and they represent, they are extracted from the upper mantle later on.
I have one.
Yeah, it's not just the Martian meteorites, even from GRS.
Sorry, yeah. I'll just ask a quick question. This is, in one of your neodymium strontium plots. Oh, sorry. Go ahead. Please ask the question. Somebody's asking a question online. Please go ahead.
Yeah, this is Neeraj from PRL. So,
hi, hello.
Hello, how are you? So, very nice talk. And I just wanted to know your thoughts about this preferential young, ages for meteorites. And as you told, Mars is largely old surface. So, what could be the reason behind that? I mean, what is the understanding behind this particular aspect?
I mean, to be honest, I have no answer to your question, but what I have read is that somehow by chance they are just sampling young surfaces. So I don't know, to be honest. I have no idea.
Yeah, but this is a very interesting aspect. I mean, and I think we should look into this. Yeah, thank you, Devashish. Thank you.
Devashish, maybe I'll ask a quick question. In your near-to-beam strontium plot, where you kind of summarize what we know of Martian meteorites, I mean, the depleted stuff are really depleted. So I'm trying to compare what we know of Earth, or what we see for Earth, and what we see on Mars. And your depleted near-to-beam values are like epsilon, near-to-beam is like +40, and Earth we don't get anything beyond +10. And your enriched is also significantly more enriched. So do you think this is just an effect of plate tectonics on Earth, where continental stuff keeps, the two M members, continental stuff in the depleted mantle, and you keep recycling continental material back into the mantle, thereby homogenizing the system more and more and making the spread less and less. Whereas on Mars, you basically still preserve those really different, M members. What's your comment on that?
Yeah, I would love to believe that. Possibly it is true to some extent, in the sense that plate tectonics and Earth has reworked, homogenized, recycled lots of material. So, and in the process, gotten rid of the some of the extreme isotopic anomalies that may have established very early on. So, as you rightly pointed out, some of the Martian meteorites have extremely radiogenic neodymium isotopic compositions, much higher than that of Earth. So they would require sources which had very high SM&D ratios. In fact, there have been works on shergotites where people have shown that you require a bit of an unusual situation in the magma ocean crystallization stage, where the SM&D ratios of the sources are actually lower than what you infer from the meteorite, so kind of. But still, the ratios that you require to form such radiogenic compositions are extremely high. I think what you pointed out may be a reason.
Okay. Do we have any more questions for Devashish? If not, thank you again, Devashish. And again, for the online audience, if you could just type in your questions, we will try to get answers from all the speakers in due course of time and get back. So thank you again, Devashish. Thank you.
Thank you all. Thank you very much.
And this is just a general announcement. Of course, we have a little bit more time until lunch. We are trying to be there at around 1. And what we could do in the next 15 minutes is maybe go over some of the questions that have been listed earlier for the earlier speakers and see if we could discuss those. Soon after lunch, we have a couple of presentations, both online, between lunch and the tea break. One is by Priyadarshi Chaudhary and one is by Vivek Krishnan. And after the tea/coffee break, the sequence in which the presentations are going to happen has been modified slightly. Instead of the first presentation after tea being by Yamini, actually Sudha will speak first, followed by Yamini, and the last presentation still remains by Martin. So I think we can just discuss some of the questions that have been asked earlier, or if you have more questions for the previous speakers, please go ahead. I mean, I do have one question for Steve. Okay, there is one question. Sorry, let me go and try to read the chat first. Yeah, I will go back to all of that. Yes, 1 second. Okay, Katrina, are you still around? If not, we will. Okay, Bhala, your question, I think we'll just copy it and maybe get a response later.
She has already answered.
Okay, fine. Sorry, my bad. Yes, sorry. Okay, earlier questions. Yeah, let me go up. So Vijay's question was, I think again for Katerina. So, do the impact triggered Mars quake at 50794A make any did it have any effect on the surrounding regions due to shock effects like boulder fall or mass wasting? And I think maybe she's trying to respond. Okay, if not, do we have any questions for Steve out here? I have a quick question, and it's a naive question, and that is, we talk about these gigantic, canyons on Mars, right? And we inferred that these were large fluid flow, right? But when you talk about fluid flow on the surface of Earth, it's purely driven by gravity, right? I mean, you need a slope, and that's how water flows, essentially. But gravity is 1/3 on Mars. And so for the same fluid, I mean, if you're imagining it's the same kind of water, right? What is your comment? How do we create something that is possibly an order of magnitude bigger than what we find on Earth, despite the fact that, the main driving force is 1/3?
Yeah, this is not quite my expertise. My understanding is you get more bed load in the, with lower gravity, you can carry more material that can do more erosion. Okay. So I think that's one possible explanation is essentially you have more material in these flows that can do more erosion. I can't say how much less erosion you get with that much less gravity, but I think it's some combination of, less gravity but more bed load.
Okay, and the same thing kind of applies for the atmosphere, the dunes, for example. You have a very, very thin atmosphere, yet you do mass transport, alien mass transport that is possibly, Earth-like or more.
Yeah, I have to say this surprises me as well, that how much aeolian activity can actually happen with that meager atmosphere. So, there's been lots of experiments done in Mars-like chambers. Of course, simulating the gravity is a little harder. One clever solution to how you experimentally simulate lighter gravity, Ron Greeley at ASU years ago pioneered the technique of, rather than using actual mineral grains, you can use crushed walnut shells, so a lower density material is used as a proxy for actual minerals. And so you take that material into Mars environmental chambers, and sure enough, you can demonstrate empirically, what Mars is showing us, that you can generate these kind of landforms, at least movements of material, even with that low atmospheric pressure. I will just repeat that it defies that you can have such thin atmosphere doing so much processing still. And by the way, you can still fly a helicopter in that atmosphere too, sure, which is yet another remarkable feature or empirical demonstration of what you can do.
Yeah, I mean,
I don't know the history of Mars that well, but as people have already said a couple of times, that Martian atmosphere was thick at some point of time. So I just wanted to know that those structures, which are equivalent to Grand Canyon structures, do we have a particular age when they were formed? And are you sure that it is formed after the thin atmosphere?
Yeah, there's obviously many different features, that I presented. The Valles Marineris system is considered, I think, Noachian in age, or at least early Hesperian. So that can form independent of what the atmosphere is doing. This was mostly a tectonic process that opened up that Valles Marineris system, and then the erosion that happened afterward can happen without atmosphere. All of that could happen on the moon if it had the right sort of tectonic process. It's the landforms like dunes. There's clear evidence that dunes are moving on the surface of Mars in the current environment. This is one of the features of some of the high resolution images that have been acquired in the last 10 years is you can actually document the movement. So the basaltic sand dunes I showed with the pyramids of Giza, those have been documented to be moving over the course of years. So there's enough, so it just goes back to there's enough atmosphere, enough wind. Now, one of the realities, and this was demonstrated from wind tunnel experiments, is to move a sand grain of a given size takes even more wind velocity. So you sort of trade the atmospheric density with increased velocity. So it takes much faster winds to move the same amount of the same sand on Mars as compared to Earth. So the slower speed winds can't really do that kind of movement, but there are enough higher speed 20 meter per second kind of winds, 20 to 40 meter per second winds that can actually pick up a sand grain and move it. And by the way, just a quick aside about if you've seen the movie The Martian and that opening sequence, that would never happen. There's simply not enough wind.
Stuck on the potato side of the stuff, right?
Now that could happen, but there's just not enough atmosphere on Mars to move a rocket like that. And an empirical sort of example of that is the solar arrays on both Spirit and Opportunity, and including the InSight mission. Those solar arrays are not sort of fixed after they're deployed. They're deployed, they flop open, and there was no wind event that ever in the 15 years of the Opportunity mission, no wind actually flipped the solar panels back up. So it's just yet another kind of example of that, there's wind, there's an atmosphere, it can move sand, but it's still very weak compared to Earth.
Okay, we can continue with the questions, but there were some comments. I do want to mention that as I said early on, that there's also a YouTube live link that has been shared with many other students who are possibly not able to ask questions, but those recordings are there. So basically, even though we are not recording it on Teams, those links will be shared with all of you. So all the talks, and if you want to go back to one of the presentations, you'll be able to do that for a long time. Okay, so I think there was a comment on whether sessions are being recorded by Renee. So I think that's the answer. And Renee was obviously very, she played a huge role to basically create, the initial material that was actually sent out to all of you. So again, from Curtin. And let's see. Are there any, I think Rahul had a question about, again, hydrous minerals on Martian surface. There was a very similar question that was asked. Yes, the detection is obviously on the surface. And that was the answer, I believe, that Stephen had given. Then deep water. Prashanjit asks whether there is any deep water hydrological budget we have on Mars. Of course, there's some detection of water ice. And even, I guess in the InSight, what Katrina was showing, there was some whitish debris which seemed like, had the reflectivity of ice. I couldn't comment on it, but it was very similar to the image that you were showing. So any comment on the water budget on Mars?
So there's been papers over the decades of Mars exploration that have tried to document and visualize what a Martian cryosphere looks like, and how deep it occurs. And so it's sort of an ad hoc explanation of how, for example, you can get these catastrophic outflow channels, these huge amounts of water that came from somewhere in the crust, in the subsurface. But there's only now starting to be radar observations from orbit that can probe at least tens, it depends on what wavelength of radar, but I guess the answer is it can only be inferred really that there are these underground and below the level of the water ice that I was showing, or the hydrogen enrichments, which is water ice just barely below the regolith. The deeper water reservoirs can only really be inferred from really the geomorphic features that we see. So you're faced with an observation of catastrophic outflow channels, for example, and one must infer where that water came from, because there's really not any measured observation that can tell you that.
I had a question related to for everyone. I mean, we're talking about the atmosphere being very thin. What about the Coriolis force? Both the length of the day is the same, but Mars is significantly smaller. How do we compare the Coriolis force on Earth and Mars? Any comments? Because that has implications for atmospheric circulation, right? So I can't think of it right now, but maybe somebody has.
This is beyond my expertise, but I know atmospheric scientists who do Mars, and there are Coriolis winds like on Earth, and so there are similar atmospheric movements on Mars, despite even in the current environment. So yeah, there's Coriolis effect.
Yeah, I mean, please feel free to discuss for another 5 minutes or so. There's also some question about outflow channels. Do we have a global aquifer on Mars? Or
I try to address it.
Just aquifers.
The answer is yes, but beyond that, it's hard to say what those really look like.
Yeah, okay. And, okay, echo. Hydrogen map, I think this is, your hydrogen map shows water equivalent hydrogen, since 1% hydrogen is equivalent to 9% water equivalent hydrogen. So you had shown a slide on the hydrogen map, whether I think it's
true.
Most likely that, yeah, it is water equivalent hydrogen. Okay. So, and okay, I think there was another comment at the end. Well, the Marsquake stuff, maybe we'll copy it and send it across so that if Katerina has some additional responses. Well, early structure, again, those are all related to. Okay, so Siddharth then mentions that lower gravity on Mars causes more dramatic geological features that remain stable over time, also lesser weathering over time. I mean, this is, I guess, in the context of preservation of large features. So, yeah, I mean. Okay, I guess you have a.
In terms of magmatism, etc., which we talk about on the moon as well. Why is the default case sort of like a single?
Oh, you mean the mantle and crustal reservoirs and using isotope systematics,
so the
right?
last slide
For Devashish's.
It could be. I mean, are there multiple or it's a single one?
Okay.
So why on the first place do you assume that there can only be single, and what is the implication if it's a single or a multiple?
I think the best answer that I have is that when we think of, we have to go back a step before and think of processes involved in planet formation or formation of planetary bodies, right? So of course, it's easy to bring particles that are microns together, electrostatic forces. I think there's still a big problem. So once a body is a few kilometers in size, then gravity takes over. So you collide and make it bigger. But there's still a problem. How do you go from millimeter-sized objects to kilometer-sized objects? Because the driving forces are still not clear. But once you start, building, body bigger and bigger because of all the debris that's colliding with, each other, and some getting destroyed, some basically becoming the big planetary embryo. The idea is we always want to start off with something that's very primitive. And so the most primitive object that we have at our disposal are some of these primitive meteorites called carbonaceous chondrites. And why do we think they're primitive? Because their composition matches the solar photosphere. And that's 99.9% of the mass of the solar system. So there is something called, for the Earth, like, a starting model called the chondritic model. So we would argue that what's valid for Earth is also valid for all inner solar system objects. That means when they grew, they basically possibly started off with a homogeneous chondritic composition. And then you start planetary differentiation. So the hafnium tungsten systematics, really date your metal silicate separation, that's core formation, because hafnium loves to stay back in silicates, tungsten goes into the core. And these radiogenic isotopes are a function of time and parent-daughter ratio. So if I can fractionate the parent-daughter elements, everything works. And then you're left with the silicate mantle. And again, they keep melting, but nothing melts 100%, right? So if you melt something 10%, then what happens is these are rocks made up of minerals, and within those minerals, you have different elements which either fit the crystal structure or they don't like the crystal structure. So essentially, we call them partitioning of elements within these minerals, right? And so, because the rocks are very similar, what happens on Earth as a fundamental partial melting process, thereby fractionating all these elements, is also valid for any other rocky body. And so the model that we developed for Earth, where we start off with a chondritic reservoir, and if nothing had happened to the planet, it would remain as a chondritic reservoir. And then, because there's melting and so on and so forth, you start having these different reservoirs. And so our understanding of other planetary bodies is also a bit biased in terms of the way we understand the Earth. But it's not a bad bias because it's made up of the same rocks and same minerals and the same starting, material too. Yeah. So, however, there are issues in the sense that we don't have to go to isotopes. There were papers from the late 70s and early 80s, and if you make a plot of aluminum over silicon and magnesium over silicon, this is important because we now have remote sensing abilities to measure these, concentrations, right? So there is something called an Earth trend. I can just draw a little sketch. And there's also something called a Mars trend based on Martian meteorites. They don't overlap. So there's always a possibility that they didn't start off with the same material. But for the sake of any discussion, this is always a good point to start because otherwise you're left with, in an unknown leading to an unknown, right? But we would rather have a model where we kind of assume, but with some discretion that, look, this is a good assumption. And so that's why these reservoirs come up because that's the way we understand the Earth. Yeah. Okay, I think it's time to get hungry. So we will just quickly walk over to the lunch.
Before lunch, we will have to have a group photo while everybody is sitting here. Okay, after that, we can go outside, but it will be better and organized.
Leave it to him. He's going to take 5 pictures in 5 different sessions. But up to him.
No, not that. Otto, please. Yeah. And for the offline audiences present here, if you have not collected the lunch coupons, please collect it from Ms. Prachiti. Okay. Okay, they will, yeah. Okay, first the photo.
For the online audience, we will restart at 2:30. So yeah, we'll be back at 2:30.